Welcome to today's event, Azure Quantum Developer Workshop. This broadcast is being recorded on behalf of the Microsoft Corporation. If you do not consent to being part of a recorded session, please disconnect your line at this time. The recording will be available at the same location you used to join today's event. To learn more about the ways you can participate in today's event, please click on the Q&A button in the lower right corner of your screen. We encourage you to interact by using the Q&A tool at any time to ask questions regarding content or to request support. Your feedback is important to us. Please take a few minutes to complete a survey that will appear as an announcement at the end of the broadcast. Thank you in advance for your support in this. If you experience any technical difficulties, please first refresh your browser. If this does not resolve your issue, please send a message and we'll be happy to assist. Now I'd like to introduce your first presenter. Krista, you have the floor.
Thank you. And hello and welcome to everyone. I'm Krista Savori. I'm a quantum computer scientist by night and the general manager of quantum systems by day. I like to dream in superposition, and I think interference is beautiful. And I believe that empowering people with the power of quantum computing today and tomorrow will be one of the greatest revolutionary steps in our history. I remember the first time I encountered quantum computing. I was sitting in Andrew Weil's seminar at Princeton in the late 90s, and I remember learning that there was a different model of computation built on quantum mechanics that enabled solving some problems that could not be solved efficiently on classical computers. And this completely overturned my notions of computation. I knew immediately I wanted to work in that space. And now, over 20 years later, we're working with a global team on bringing this technology to life. Today, I want to thank you personally for showing up, for leaning in during what continues to be an unprecedented, challenging time. I recognize the added challenges you may personally be navigating, and I appreciate you dedicating precious time and spending it with us today. Today, we will take a virtual journey together, a journey to scale. Our journey navigates through three key areas. First, solutions to planet scale challenges require us to reinvent computing. Quantum computing promises the answers. Second, reinventing computing requires reinventing the full stack in order to realize the full potential of quantum computing. And third, it's through this reinvention that we've discovered how to achieve impact today as well as tomorrow, and learn that innovation scales with a vibrant developer and partner community who are also innovating at scale. Our journey will help you better understand the quantum road ahead, what can be done today, what will be enabled tomorrow, and how you can prepare for both the present and the future. We'll also touch on our unique approach today, our approach at Microsoft to scalable quantum computing, and how you can get started with quantum development and quantum impact. My hope is that today's journey inspires you to get started and to join us in innovating for the next era of computing. The path you take from here is personal. You may start by using Azure Quantum to achieve new capabilities, to have real impact today. You might choose to explore and learn quantum programming, how to process quantum programs through Q# and Azure Quantum onto quantum hardware, with an eye towards maturing your skills as this technology matures. You may even use your learnings to catapult into the next exciting chapter of your career. And with each path, we hope you join the growing quantum community and join us on this quantum journey. Now, while you're on today's journey, I have an ask of each of you. Please be respectful, encouraging, supportive, and inclusive of others. Help cultivate the inclusive community we aspire to have for quantum computing. And with that, I'd like to start you on your road to quantum and turn it over to your facilitator for the day, Matt Zanner, our developer outreach lead. Matt?
Thank you very much, Krista, for those inspiring remarks. I really appreciate you setting the tone properly for today, and we're excited about the day ahead. Hello, everyone. I'm Matt Zanner, and as Krista mentioned, I'll be your host of sorts for today. I work on our quantum systems engineering team, looking after developer outreach and engagement. And hopefully I'll act as a common reference point for you today, along with a small army of subject matter experts behind the scenes also working to address your questions in chat as we go. So first things first, let me share my screen. As Krista mentioned, we adhere to a code of conduct for all of our engagements, promoting a welcoming, safe environment for everyone. And we request that you do the same and be respectful during this event. Now I want to take you through what the day looks like, okay? So we have Rockstar colleagues joining us from around the globe today to deliver a live, rich set of content and experiences. As every journey needs a map, you'll see this graphic throughout the day to help you keep track of where we are in the content and have visibility to what's ahead. We'll start with a quick overview and give you a sense of how we view the path to scalable quantum computing. We'll then go a bit deeper and we'll start to cover Azure Quantum as our new service on the trusted, familiar Azure platform. One of the key Azure Quantum solution areas is optimization. So we'll be spending some focused time understanding optimization theory and capabilities and how you can use that to make impact today. We'll then enjoy a bit of an extended break, give you a chance to get a bite to eat, catch up on some work, and hopefully refresh for the afternoon. We'll rejoin at 12 noon Pacific time and start taking a deeper look at another Azure Quantum solution area using Q# programming language to characterize problems for quantum hardware execution. This will help you prepare now for what tomorrow will bring. This will then take us to what may be the main event for the developers joining us today. We'll have a virtual lab where you'll be walked through actual coding exercises with various algorithm examples. And if you like, you can follow along with your own local environment to help you learn the skills hands-on. After another short break, we'll share the various resources and guidance available to help you learn quantum and start on your path, expanding your career. And our final session will pull us back up a bit and highlight some great personal examples of what building a community for quantum actually looks like, and hopefully serve as a final shot of inspiration in your arm to join us on this journey. So without wasting any more of your time, I'd like to welcome Julie Love to take us through the content. Julie, please take it away.
Thanks, Matt. So thank you everyone for joining. We have an exciting day ahead of us. I'm Julie Love. I'm a quantum physicist and lead the quantum applications group at Microsoft. I caught the quantum bug over 20 years ago when I took the first class in quantum computing ever offered at MIT. And it was mind-blowingly exciting, but the impact from quantum at that time still felt really far away. And now I lead a team really focused on solving the world's most complex challenges and delivering quantum impact today for customers, partners, and developers. So I'm going to go ahead and share my screen and walk through the agenda for the next few minutes, the next 20 minutes or so. Let's sort it out. Okay, so let's see, Matt, can you see my screen?
Looks great, Julie, thanks.
Perfect. So I'm going to spend the next 20 minutes talking about, before we get into the detailed programming sessions, I'd like to take a moment to frame the opportunity that quantum represents for all of us, what Krista talked about at the beginning. Quantum has the potential to truly redefine how we think about computing for our toughest compute challenges. I'll walk you through the Microsoft approach to quantum computing, how we are architecting and building our quantum systems to scale to the size required to realize the full potential of quantum computing. And lastly, I'll talk about what you can do to get started right now and experience quantum impact today. So why should we care about quantum computing? Well, despite all of the advancements that we've made, In compute, and with the power of the cloud, there remain problems that we won't ever be able to solve, even with all of the compute power we have. Many of these problems are planet scale, impacting our environment, our energy systems, our food supplies, healthcare, and more. And quantum computing is this technology that a number of us scientists and technologists are looking at to help us solve some of these problems because of its ability and promise to solve a selection of hard compute problems exponentially faster. And that's because it's a truly different way to compute. Quantum computing speaks the language of nature. It's how atoms and molecules work. And with this power, we have the opportunity with quantum to redefine the meaning of computing to address planet scale challenges. So quantum computers will be really good at solving big compute challenges. So problems where there's a small amount of data, but a high amount of compute required. Problems that exist in chemistry, material science, cryptography, machine learning, and more. So let's take one of these examples. Nitrogen is critical for healthy soils and high plant yields. We create artificial fertilizers that add nitrogen to the soil at the industrial scale using a process invented in Germany over 100 years ago called the Haber-Bosch process. It's an industrial process requiring high temperature, high pressure, and it consumes about 3% of the world's natural gas. But we know that plants can do this on their own. There's an enzyme produced in the roots of the bean plant that acts as a catalyst to fix atmospheric nitrogen into the soil. If we were able to mimic and reproduce this biological nitrogen fixation at scale, perhaps we could create fertilizers that reduce our demand on the world's natural resources and help us more sustainably feed a growing human population. And the challenge to mimicking nature at scale is to find an efficient catalyst. But this is a really hard thing to do. Today, catalyst development is done by expensive, time-consuming experimental trial and error through lab experiments. A catalyst is proposed by a chemist, and then they have to find a way to synthesize it, produce it, and experimentally test it. This process has to be repeated over and over for tens of thousands of catalysts. Well, we can simulate some of these chemical processes using high-performance computing, accurately simulating a molecule as complex as the one in biological nitrogen fixation and all of the quantum level correlations present in these molecules. It would take our classical computers hundreds of millions of years, if not billions of years, to run that computation to the accuracy required to be able to design a viable candidate molecule. Quantum can help us address problems like this that we previously thought were classically completely intractable. So here I'm showing, we can talk about these timescales required. So here I've got a chart showing calculation time, and my time here is going to run from seconds to the age of the universe. And along the x-axis, I've got number of atoms, or complexity of these molecules. So when we look at a chemistry simulation, like understanding the way that biological nitrogen fixation works, the scaling is exponential. And even with continued improvements in classical computing performance, moving to exascale computing and beyond, we can make changes to this curve. But it's an evolution of the curve. We can move it over to the right slightly and bring these timescales down. But when we can leverage the power of quantum physics, when we can have a computer that speaks the language of quantum, we have a chance to fundamentally change the curve. We have the opportunity to take problems that scale exponentially and convert them into polynomial time. And this is because quantum computers operate on different principles than classical computers, natively speaking the same language as nature, which is quantum mechanics. They'll be able to mimic these reactions and allow us to have the tools and capabilities to study and design new compounds, effectively offering us a path forward through which we can address planet scale challenges. And so these big compute challenges show up in chemistry, material science, cryptography. The potential of quantum is limitless. At Microsoft, our mission is to empower every person and organization on the planet to achieve more. With this in mind, our quantum computing efforts are really focused on exactly that, solving the world's most complex challenges by developing the most impactful and scalable quantum system. And we're focused on delivering this technology to bring together the next generation of quantum engineers and developers to drive this innovation and help realize the full potential of this technology. We have to do this together. So what does it take to solve these planet scale challenges? Well, it takes building and scaling the entire quantum stack. This has been the driving force for our team at Microsoft for nearly 2 decades. We've been collaborating with the global quantum community to advance and scale every single layer of the quantum stack, from the quantum hardware to the control plane, up through the software, tools, and applications, to make sure that we're bringing you the tools and capabilities to go unlock solutions to our most pressing challenges. And it takes a deep understanding of every layer of the stack to be able to get there. We have to design each layer for scale. For example, deeply understanding the algorithms and applications. So the example I just gave you, nitrogen fixation. Understanding that deeply, implementing that algorithm in code, gives us a level of understanding of what we need from the quantum hardware. We need the quantum hardware, so qubits are the fundamental building blocks for quantum computers, but they're inherently really fragile. We need the quantum hardware to stay quantum long enough to get through these interesting, world-changing applications. So we require more from our qubits. We're developing nanowires that allow us to encode the quantum information into the material itself, where the qubits become more robust to noise and we don't need as much physical hardware to get to that scale required. And our understanding of how quantum computers will solve these problems has led to breakthroughs changing the way we think about solving these problems. And we've discovered that we can already use these quantum methods today on the hardware that we already have in Azure with what we call quantum-inspired methods. So you're going to hear more about those methods later today. So I want to speak to some of the elements that we've been working on to scale across the layers of this stack to get to millions of qubits and beyond to deliver the type of impact that quantum has promised us. So let's start with the qubits. The fragile nature of qubits, this basic information building block, is well known as one of the most significant hurdles in producing a scalable system. Even the slightest interaction with the environment can cause the qubits to decohere or collapse, and we lose our quantum information. We're addressing this fundamental challenge, this fragile nature of qubits, by developing a revolutionary topological qubit. And we're building it out of these strange particles that were predicted back in 1937 by an Italian physicist, Ettore Majorana. So I'll talk you through how this approach is really different and leads to more scale. So if we think about a typical quantum particle, like an electron has a charge and an intrinsic property called spin. And you can think about spin as a tiny magnetic dipole moment. And like a classical bit, the spin can be pointed up or down. So bits, regular classical bits can be 1 and 0 or on and off. But quantum bits have this special property that they can exist in superposition. So they can be more than just 1 or 0. So this bit is in a superposition of up and down. When I measure it, I'll get 1. I'll get up or down. But in its quantum state, it can be in the superposition. So 70% of the time, I'd measure this qubit to be up and 30% down. So it's in the 70-30 superposition. But as you can see, it wiggles a little bit. There's some noise around its average direction. And this noise is unavoidable when we store this information in a local system like a single electron, because there's always other electrons nearby, all with spin, which like magnets, are all interacting with each other. So this information that I'd originally coded in a single electron, the spin superposition of the electron, leaks out really, really quickly to all of these other spins. So we lose our quantum information really fast. And this is generally true. Quantum information leaks away really, really quickly, making long calculations really difficult. But there's an exception. And to illustrate this, we can think about a train. So we've got this train. Now we've frozen out the degrees of freedom of the individual cars in the train. And the train is now, each car is tightly bound to the neighbors. And the train moves as a single unit. And only the engine at the beginning and the car at the end have some freedom for a little bit of extra motion. So this is the start of the idea behind our qubits. Can we realize this frozen state with electrons, and it's all in a single row, with the electrons completely frozen out in the middle and only the end electrons that can wiggle a little bit. So this was exactly Majorana's idea, Ettore Majorana, this Italian physicist back in the 30s. He imagined a single row of electrons, like I've shown here in this nanowire, occupying all sites in a row, except for the one at the end. So I've got an empty spot right there on the left. So now imagine you're sitting in an auditorium. Maybe you remember when we used to watch presentations like this in person. And you're in an auditorium and you're in a long row of people and you've got an empty seat at the end and the entire row is filled with people. Now imagine everybody stood up and moved over one seat. From the perspective of the empty seat, your collective motion causes a huge jump all the way to the other end of this empty seat. And we could repeat this, we could move back. And this, when we move back and forth, this collective motion causes this empty seat to make this massive jump all the way to the other ends. As I just showed you with quantum physics, we can have this state exist in superposition. And this superposition looks like we've broken or fractionalized the electron into two pieces. And the two pieces then are separated by this long physical distance. And when we do this, we effectively disconnect our quantum states over this long distance. And this noise that interacts with the qubit that tends to have our information leak out very quickly can't understand what's happening at both ends. You need to know what's going on at both ends of this. And so this gives us what's called topological protection for this information. And so the two end states, we call them these Majorana particles, named after Ettore Majorana. These were predicted in 1937, and we've experimentally realized these Majorana particles in our labs. And this is exactly how we're building our qubits. We make these nanowires where we can create these Majorana states at the ends and topologically protect the quantum information. And so why is this important? Well, as I showed you earlier, with qubits without this protection, correcting for the fragile nature of qubits requires significant redundancy in the hardware. We can't do error correction the same way that we do classically because we can't copy quantum information. And so we can have a large ensemble of qubits to encode that information and to do error correction. When we have topological protection, we need far fewer physical qubits to realize a computational logical qubit, which allows us to scale to the millions of qubits required for commercial applications in a scalable quantum computer. Okay, so let's keep going through the stack. Qubits are just one component of a much larger system. You know, think about a car. It's much more than the pistons and the engines. The quantum computer is more than just the qubits. We have to think about scale across every single layer. The control systems, the software and tools to process the jobs, the applications, and perhaps the most important, the partner ecosystem and the developer community who will utilize these tools and help improve solutions and drive this innovation at scale as we progress on this journey together. So I'm going to go through a couple more elements of the stack. So layer up from the qubits in quantum hardware sits the control interface, which connects the quantum hardware with the classical computer. We have to do this control over a huge temperature differential. These quantum states exist only at very low temperatures. We operate our quantum states at about 15 millikelvin. It's more than 200 times colder than deep space. And we need to communicate this with these qubits from the data center, so an environment that's hot and noisy. At our quantum lab in Sydney, Australia, we've demonstrated this control technology with a brand new cryogenic chip that can scale up to 50,000 qubits, to control up to 50,000 qubits, using only 3 wires. This is super important as we think about communicating with these qubits and not adding heat and noise from room temperature and massive numbers of cables. And we're bringing this technology, the qubits, the control systems, the software, and the programming languages together and bringing that into Azure Quantum. We're enabling quantum computing as a service with Azure, which brings the familiarity and scalability of Azure, the world's computer, with the quantum tools and capabilities to make it easy for you to get started and to have impact. We're bringing our topological qubits to Azure Quantum, and we're doing this together with partners. We've partnered with hardware providers, quantum hardware providers, including IonQ, Honeywell, and QCI. And we've partnered with 1QBit to bring software solutions. It's an open ecosystem bringing together the world's most diverse and robust ecosystem of quantum hardware, quantum software, and quantum solutions. And it's here today, ready for you to build solutions on so that you can have impact today, now, and into the future. And we've built and open sourced our Q-Sharp development environment together with the Quantum Development Kit to provide you with a high-level programming language, libraries for use in scalable algorithm and application development. Q-Sharp enables you to get started today writing programs for quantum hardware that we have in Azure, as well as the quantum hardware that we will have in the future with scalable quantum systems. You can write code once and run it across quantum hardware and simulators of quantum hardware. So you might be asking, why should we get started programming with a new programming language today if quantum hardware is still in the early stages? I'm guessing because you're here, that you're interested in being one of the early adopters of quantum. It's important to prepare now because hardware is evolving rapidly, and preparing now allows you to learn, characterize, and write quantum algorithms for the hardware that we have today, and be able to test them against real quantum hardware, quantum simulators, and accelerate your adoption as technology evolves, getting faster time to impact. And the other reason it's important to start now is it's going to take us time to understand these algorithms. For example, the resource estimators that we've released allow us to understand the time it will take to run an algorithm on a quantum computer that hasn't even been developed yet. So for the example that I gave earlier, talking about nitrogen fixation and having an algorithm to understand and design a catalyst for nitrogen fixation, our first cut at the runtime of that code when we wrote it for a quantum computer was hundreds of thousands of years, which was already amazing because the classical algorithm is going to take billions of years, but certainly not short enough to be useful. So we can use tools like resource estimation to see what's consuming the resources, optimize the code to be more efficient, to run faster. And now we have code that we believe will run in days on a future quantum computer. And this is a really exciting field that's emerging of quantum software engineering. So I talked a little bit about the stack and the scaled quantum system that we're building, but this is all useless without you, the community of developers and a vibrant partner ecosystem. We have to figure out how to do this together. Working together with our partners that I mentioned, 1QBit, Honeywell, and QCI, we're assembling the most diverse selections of quantum solutions, software, and hardware across the industry to bring about true quantum impact and continue to innovate at scale. And we've been listening to you from the start. Our progress has benefited greatly from your contributions. We initially established the Microsoft Quantum Network to empower a broad community of organizations and individuals to get involved. Listening to this community helped guide our efforts to open source our developer tools, which are now more useful and complete as a result of direct contributions from you in this community. And Azure Quantum is being built based on your needs that you've expressed to us to get started and desire to explore what it means to develop for and target quantum hardware today. Our Microsoft Quantum Network ecosystem spans hardware and software solution providers, customers, developers, universities, representing a comprehensive engine of innovation. This vibrant developer community serves as fuel for the engine and helps us realize our collective vision of scaled quantum computing. So I'll give you a few examples of partners and companies that are having impact. The ecosystem really is driving this impact with a focus on optimization today, searching for ways to improve and speed up algorithms, leveraging quantum-inspired solvers. I talked about these earlier, where we can run these quantum methods already today in Azure. OTI Lumionics are making breakthroughs in fast materials design, using quantum-inspired optimization to simulate the quantum processes that cause light emission in a material used in OLEDs. 1QBit's using these QIO, quantum-inspired optimization solvers, to drive innovation in drug discovery and material science. And JIJ is using Azure Quantum to optimize traffic lights with their customer, Toyota Tsusho. Behind each of these examples and many more are quantum software engineers, developers, algorithm designers, using optimization as a starting point to realize quantum impact today. So the power in the technology lies not in the technology itself, but what it enables us to do. Massive technology shifts span several time horizons, and it's helpful to think about quantum in this way as well. We are in a journey together across these horizons. So today, together with our partners, we're bringing to market decades of optimization research in the form of quantum-inspired optimization solvers that are accessible through Azure Quantum. As I shared on the last slide, customers and partners and developers are using these capabilities across industries to realize quantum impact today. Also available through Azure Quantum and the Quantum Development Kit, developers can code quantum algorithms in Q#, test these algorithms on quantum simulators, and execute jobs on partner quantum hardware. With these capabilities, you can explore how to utilize quantum hardware today, learn and evolve your skills, and prepare for tomorrow, when we realize our collective vision to scaled quantum computing to be able to solve some of the most pressing planet-scale challenges with a vibrant partner ecosystem and developer community. So what can you do to get started? Well, today is a perfect starting point if you're new to this field. You can sign up and become an early adopter of Azure Quantum, start exploring and using optimization solvers today to drive immediate impact for your business. Start evolving your career and developing new skills by using Q# and experiment with quantum algorithm development and quantum hardware. And join our global developer community to help accelerate innovation in the field and further our collective understanding of how quantum hardware can be used to solve our toughest compute challenges, leading us to tomorrow where we will be able to collectively realize impact at scale. So thank you so much for joining us today. I'm excited about what the day holds ahead and what you will do with this technology. And with that, I'm going to pass it over to Matt.
Thank you, Julie. If you could advance one slide, that'd be great. Awesome, thank you. So next up on the agenda, we'll now dig in a bit more on Azure Quantum and hopefully help you understand better what exactly is Azure Quantum and what you can do with it today. So let me please welcome Mike Bluen. Mike, if you're there, please take it away.
Hi, everyone, and welcome. I am Mike Bluen. I'm a senior program manager on the Azure Quantum team, and I am really excited to give you an overview of Azure Quantum. So let's get started. My job today is really as a tour guide. So I'm going to be giving you the lay of the land, as it were, to help you get the most out of the rest of your Azure Quantum developer workshop. So I'll give you an overview of what we'll cover today, then direct you to some of the sessions later where we'll be going much deeper on all of this information. To start with, I'll give you an overview of why we built Azure Quantum, and then I'll introduce our two main solution areas, optimization and quantum execution. I'll provide a quick demo of how you can create and manage an Azure Quantum workspace in the Azure portal, and then I'll follow up on that promise to help you get the most of your developer workshop by pointing you to some of the later sessions where we'll be going much deeper on all of these different topics. So let's start by talking about why we built Azure Quantum. And in short, the answer is to empower the global quantum and business communities with access to state-of-the-art hardware, solutions, and learning materials to start your journey. So whether you're just getting started learning quantum or developing quantum algorithms and applications, or whether you're a business and you're trying to apply quantum technologies or hardware to solve difficult problems in your line of business, we built Azure Quantum for you, and in conjunction with the learnings that we've had working with our MQN partners and a whole bunch of different companies in this space. But it all starts with access to quantum hardware. We believe it's critical that you have access to the leading hardware technologies of today. And as Julie mentioned earlier, this technology is in very rapid development right now. And so we are committed to evolving the generations of hardware and technologies that are available through Azure Quantum so that we can truly be your one-stop shop to get access to the most wide variety of quantum technologies, especially as these systems continue to evolve over time. And one thing that I think is really exciting is that all of this is made uniquely possible by Q# and the QDK. And if you don't know already, Q# and the QDK are Microsoft's hardware agnostic quantum programming language and quantum development tools. And they make it really, really easy to target programs across different hardware providers and across different technologies. And it also makes it really easy to adapt your programs to new technologies and to more scalable quantum systems. But you can't talk about Q# and the QDK without talking about the wonderful quantum community that we've built since the release of the QDK in 2017. And we're committed to giving back to this community by developing learning materials and resources and samples that will be widely and freely available to everyone in the community. And so if you've already gotten started on your quantum journey, you're probably familiar with things like the quantum katas, which help introduce topics in quantum computing, as well as help you learn how to build quantum programs in Q#. And we're continuing to develop new learning materials, new resources, and new samples to help you get the most out of it. And in particular, we're really interested in dispelling this misconception that you need to go out and get a PhD in quantum physics or in quantum computing in order to get started with quantum development. And that's simply not true. So we want to make sure that you have all of the materials available to you today so that you can go ahead and get started, whatever your experience with quantum is. And so whether you are a developer today, or whether you're in academia, or you're a student, or whether you haven't got any experience in computing and programming, we want you to be able to get started. And we also have a number of key partnerships with universities to help develop quantum courseware to bring and develop the workforce of tomorrow. And all of this is expanding on the successes of our MQN partners that we've been learning with and partnering with for a long time now. And this is a group of companies, as Julie mentioned, that are developing quantum technologies or working to apply quantum to their regular line of business. And if you want more information, I suggest you go check out the recording of Julie's talk to learn a little bit more. But it's through working with these companies and listening to their needs that we understand that businesses today need to solve difficult problems today. So we aren't just bringing quantum hardware to Azure Quantum, we're also bringing a suite of optimization technologies that are designed to help you have powerful impact today. Because we believe that becoming quantum savvy today is going to pave a strong path towards utilizing a scalable quantum system when it is available. And of course, we're really excited to be working with our key partners, 1QBit, Honeywell, IonQ, and QCI to reach their customers at Azure scale. So let's go ahead and talk about the two main solution areas coming to Azure Quantum. The first is optimization. As I mentioned earlier, this is really all about having impact today. And so we make strong use of classical technologies like CPUs and FPGAs that are widely distributed in Azure data centers. And as quantum technologies continue to develop, these types of problems will also be adaptable to those technologies in the future. And the second main area is quantum execution. And quantum execution is all about writing and running quantum programs. And this is all, and you can get started with quantum execution today and help prepare for our scalable quantum systems of tomorrow. Let's take a little bit of a deeper look at these two areas. We'll start with optimization. So as I mentioned, optimization solutions today often make use of the silicon-based architectures widely available in Azure data centers, and they're brought to you by a partner ecosystem of solvers. These solvers come from unique algorithms developed by Microsoft as well as their partner 1QBit. And the whole idea behind optimization is that you describe a problem using the cost of a solution in different potential configurations. A really simple example of this is the classical traveling salesperson type problem. And in this problem, you have a salesperson and they need to visit a number of different cities, and they're trying to find the most efficient way that they can do so. And you can imagine modeling the cost of a solution based off of the distance that they travel, or the amount that they spend in airfare, or perhaps their carbon footprint as they go between all of these different cities, or maybe a combination of metrics. And so in this case, we've described a problem based off of how it costs or what parameters we're interested in optimizing for, and then you submit it to one of these solvers to generate a good solution. But these types of problems are common in many different industries and in applications. One example is of unit commitment, which is a type of problem that's very common in the utilities sector. Another example is material science. If, say, for example, you were looking to develop new materials and optimize or minimize certain properties of those materials, oftentimes these problems can be expressed as optimization problems. And there's many other potential industries and solution areas that can benefit from these optimization techniques. But one thing that's really exciting is, as I mentioned earlier, because oftentimes these technologies are using classical compute, that we can scale it to your particular business needs and take advantage of Azure's advanced architecture to maximize resilience, because we are building on these technologies that we know and understand very, very well. And these optimization techniques have already powered strong, proven results with our MQN partners, such as OTI, 1QBit, and JIJ. And if you're interested in these particular case studies, go and check out some of the materials that we released at our Build conference in May, where we talked a little bit about what these partners were able to achieve using optimization through Azure Quantum. And I want to direct you, if you do want to learn more about this particular solution area, to the next talk by Anita. And she'll be going a lot deeper on optimization, how you create an optimization problem and how you describe a real world problem like this, and then how you can use Azure Quantum to generate solutions for that problem. She'll also be giving you a bit more of a complete list of the different industries and applications where optimization can have impact today. Next, let's give an overview of quantum execution. Now, quantum execution is all about building quantum algorithms. This means writing your programs in Q#, which, as I mentioned, is our hardware agnostic programming language. You can develop with local or cloud simulators and resource estimators, and when you're ready, you can run against hardware in Azure Quantum. This is all using our existing tools in Q# and the QDK, and it's a high-level language, which means that you don't need to worry about the particularities of the hardware that you're developing for. Instead, you worry about the algorithm that you are trying to build, and you can benefit from things like library support. As I've mentioned a few times, it's hardware agnostic, and you can develop with it in your favorite development environment. So Visual Studio Code, or Jupyter Notebooks. Or if you have a different environment that you can prefer, you can use our command line tools combined with whatever environment you like. And this is all freely available and open source on GitHub today. And it has a wonderful and vibrant Q# community and plenty of learning materials and quantum katas to help you get started today, independent of how much experience you have in quantum already. And if you do want to learn more, I'll direct you to Megan's session a little bit later this afternoon. She'll be providing an overview of Q# and quantum execution and kicking off the second block of the Azure Quantum Developer Workshop, which is entirely focused on quantum execution. But I can't talk about Azure Quantum without mentioning the amazing platform that it's built off of. Azure Quantum has been built from the ground up to give you the best of Azure, including the security and privacy and control of your critical data and processes that you expect from Microsoft. From a security perspective, that means that we have things like role-based access control built in that provide a simple but extensible security mechanism that prevents you from having to do things like manage sensitive access tokens. Using these systems, administrators are able to control access to quantum solutions and programs and data and the results that are important to you, and make sure that this never is leaked out of your control. Of course, every action in Azure Quantum is logged and auditable, again, to ensure the control of your critical data and processes. The other benefit of using Azure Quantum is that all data is automatically stored in Azure storage, so you never lose a key result. And in fact, every single input and output from Azure Quantum will be automatically stored there, so it's easy to both correlate things as well as to share data and results with other coworkers who may be using the same workspace. And all of this is made available to you on a familiar and trusted platform, so you can take your first step with Quantum, using the familiar Azure usage-based pricing, the Azure portal, and the best-in-class tools that you've come to expect from Azure, including CLIs and SDKs. And all of this is backed by Azure support and by our partners to help ensure that you have the support that you need to be successful. So let's go ahead and go into a short demo of how you can manage an Azure Quantum workspace in the Azure portal. So I'm going to bring up the Azure portal here, and as you can see, I've already got the Create Quantum Workspace flow open. We're going to get started by providing a few pieces of basic information to help organize our usage of Azure Quantum. The first thing I'll do is select a resource group. And if you aren't already familiar with Azure, a resource group is like a file folder. It helps you organize the different resources that you've deployed in Azure, and it's purely a construct for your own organization. I'm going to apply a name to my workspace. I'll call it mbluin Azure Quantum Developer Workshop, and that's a bit of a naming convention that my team uses. And I'm going to select the region to deploy my workspace in, and this is going to choose where my data is stored. As I mentioned earlier, all of my data is stored in an Azure storage account. So I'm going to go ahead and create a storage account to hold all of this data, and I'll give it a name there. And these look like pretty good defaults. So I'll go ahead and accept that and make sure I'm linked up to that newly created storage account. Okay, that's all the basic information, but let's get to the more interesting part, which is the different providers that we've made available to you. In Azure Quantum, you'll have access to solutions from 1QBit, Honeywell, IonQ, and QCI, not currently pictured, all through a single convenient workspace. So I've gone ahead and added all of those different providers. And of course, all of the pricing in Azure Quantum is usage-based, so you're going to be charged after you create some amount of usage. The next thing I'll do is go ahead and create a tag, and this is another organizational feature that let me organize my resources, and it's particularly useful if you are using Azure in a larger organization or an educational institution. Lastly, before I go ahead and create all of this, I'm going to review my selections. And one thing that's really great about Azure Quantum is that the terms and the providers that you're working with, you actually have a direct relationship to them. And so that means that every time you, for example, run a quantum program on Honeywell, IonQ, or QCI, you are working directly with that provider. You're running on their quantum system. And if Microsoft's not able to support you, they're able to help pitch in and make sure that you have all of the support that you need. So I'll go ahead and create the workspace, but instead of waiting for that to complete, I'm going to jump over to a workspace that I had previously created for this demo. In this workspace, you can see a bit of the basics information that I had picked earlier. And I'm going to jump in and look at the access control solution. And I mentioned this earlier. This is the role-based access control that is available by default in a Quantum workspace. And I want to unpack this term, role-based access control. What does that mean? Well, essentially, it means that your administrators can define different roles, and a role specifies what purpose each individual in your team does, and it has certain permissions associated with it. And if I look up my own permissions on this workspace, you can see that I'm both a contributor and an owner, and together those roles mean that I can basically control this workspace. This mechanism makes it really easy for your administrators to go in and control access to the sensitive solutions and data that are important to you. The last thing I want to show you today is job management. So a little bit earlier, I had gone in and run a bunch of QIO problems. So you can see I was trying to solve this here. I'll pull up the last solution that I had. And you can see all of the metadata, so you can see when I had gone and run this problem. And as I've mentioned a couple of times, all of the input and output from my jobs are correlated together and available online through Azure without having to download an SDK or a tool for the rest of your team to have access. All right, there's plenty of other features in the Azure portal that are available, but I will leave those for some of our later speakers to get through. And I want to come back and provide a quick summary of what we've talked about today before directing you to the later sessions in the developer workshop. So to summarize, Azure Quantum is built to empower the global quantum and business communities with access to state-of-the-art hardware, solutions, and learning materials to start your quantum journey. This means that Azure Quantum provides access to the latest quantum hardware, and it's already backed by a wonderful community of Q# developers. We also have our optimization techniques, which allow you to have impact now. And they're built on the proven results from our MQN partners, 1Qubit, JIJ, and OTI, as well as others. And these are offered at the scale and robustness that you would come to expect from Azure. Our quantum development and execution solutions make it possible for you to run quantum programs on real quantum hardware in order to poise yourself for scaled impact tomorrow. But of course, you can get started with the Q# and the QDK, which are available today, as well as all of the different learning materials that we've already built out and made available to this community. And all of this is built on the trusted Azure ecosystem that you're already familiar with. And we have security and privacy of your data top of mind. We've enabled painless collaboration through Azure Storage, and it's all backed by usage-based pricing, supported by Azure Support and by our partners. So with that said, I wanted to call out those two sessions that I talked about a little bit earlier. The first is the optimization deep dive. So if you are interested in learning more about optimization, the types of optimization problems that you can solve, how you make an optimization problems, and how you can solve it in Azure Quantum, be sure to check out the next session coming up in just a couple minutes from Anita. And if you're interested in learning about quantum execution, be sure to focus on the session just after the break, which will be hosted by Megan, and she'll be giving you an overview of Q# and quantum execution. This is going to start out a whole afternoon of activities designed to help you get started with Q# and the QDK. So thank you very much. I'd like to hand the mic back over to Matt.
Mike, thank you so much for a great session. If you could just advance your slide one click, that'd be great. Thank you. So as Mike mentioned, in a moment, we'll be diving right into our next session here, where we will go deeper on optimization, right? This is clearly a solution area that can drive some very real impact today based on the previous sessions. And we're excited to share some more detail with you. Before we do that, just a couple of housekeeping notes. So lots of questions asking about the content being available. We will be providing all the sessions that you're participating in today on demand, and we hope to get those up as soon as possible, most likely by Monday the 20th at the latest. And you'll simply be able to go back to the original registration page link to access that content. So we'll make sure we cover off in the closing remarks today with specific guidance around that, but wanted to let people know that will be available and ready for your consumption afterwards, if you need to go back and revisit any of the content that's been shared. Next up, there are a lot of sort of general questions about our position around quantum and some of the points that Julie covered in her earlier session. Just please encourage you to go to our Microsoft Quantum website, which is a great starting point to dive into not only the background of our capabilities and solutions, but also specifically into areas like Azure Quantum and whatnot. And with that, Anita, if you're ready, I wouldn't mind starting just a minute early, and we can make sure that we've set ourselves up for success for the rest of the agenda. And I'll turn it over to you.
Sounds great, Matt. Thanks. Let me get my video up. All right. Well, it's been really interesting so far. I hope you're belted in and ready for a bit of a deep dive, because we're about to hit a deep dive onto the optimization service available through Azure Quantum. First, though, a little bit about me. So my name is Anita Ramanan. I work as part of the Microsoft Quantum team here. I'm a quantum software engineer, and my job mainly focuses on building tailored optimization solutions for our customers. For example, the traffic minimization case study with Ford, which we'll explore a little bit shortly. I also spend lots of time talking to people such as yourselves who make up our wonderful quantum community. Now today, I'd like to build on the information that you've probably seen before at Build and like in similar events, and give you a deeper introduction into how you would actually use our Azure Quantum optimizers to solve an industry problem. In this instance, I'll be focusing on something called job shop scheduling. I challenge you to say that 3 times quickly. And I'll wrap up with some more examples of other industry applications to get your ideas flowing. All right, so Mike just covered this, so I won't spend a lot of time repeating. I just wanted to reiterate that Azure Quantum suite of optimization solvers enables you to have real impact today. These solvers run on classical hardware right now, and some may be adapted in future to run on quantum hardware once this is available at scale. Now you can access these solvers using a classical language such as Python, which you'll see me using in the demo later. The key thing here is that you aren't responsible for writing that optimizer code. Instead, you just need to learn how to represent a problem in that particular type of format that the solver will take as input. Today, I would like to introduce you to some of the tools that you'll need to do just that. All right, so before we get stuck into how optimization in Azure Quantum works, let's take a second to define exactly what we mean by optimization in the first place. At its simplest, optimization is just the process of selecting the best thing from a set of possible options. We can define best in many ways. It could be the option with the lowest cost, the quickest runtime, or perhaps the lowest environmental impact. To speed things up, we usually just generically refer to this definition of best as a cost to be minimized. If we wanted to maximize the cost instead, for example, if we wanted to maximize the energy output from a solar cell, all we would need to do is to multiply the cost by -1 and then minimize that. Now, usually when we say we have an optimization problem, we mean we have a pretty complicated one where lots of variables can interact in many ways to influence this final cost. We call a particular arrangement of these variables the configuration of the problem. Now, because there are so many possible configurations to choose from, it gets really hard for us to identify the best solution, particularly when the problem space is really large. It can be easy to get stuck in local optima, like we see here. The way the cost varies as a function of these different configurations gives us what we call the cost function, this nice big wiggly line on our graph. So let's illustrate this with an example, in this case, traffic minimization. Now the aim here is to reduce congestion in our road system in order to reduce the amount of time that we spend sitting in traffic, which for me personally is always a good idea. Now, each configuration here represents a different combination of routes that we have assigned to each of the cars in the simulation. The cost is the overall traffic level or congestion level, which is what we're looking to minimize. So you can see in these kind of 3 pictures highlighted some examples of different possible system configurations, and each of these have different cost values. The redder the road segment is, the higher the traffic or congestion level, and therefore the greater the cost. As you can see in this example, this particular configuration is highly congested. There's lots of red everywhere, meaning that there's lots of cars on the same segments of road, which means that lots of traffic builds up. We move slowly. This is why it lives a bit higher up on our cost function in terms of the cost here. This configuration, on the other hand, is much lower in congestion. It's kind of much greener or less red. The congestion is lower. We've minimized the cost, and thus it lives kind of lower down on our cost function down here. So how do we actually tackle these optimization problems? How do we avoid getting trapped in local optima such as these, and thus find good solutions to our optimization problems? There are many ways that we can tackle them, ranging from purely classical methods such as taboo search and simulated annealing, through quantum-inspired methods such as substochastic Monte Carlo and simulated quantum annealing, through to purely quantum optimization techniques, either running on quantum annealers or on circuit-based quantum computers, for example. As you might guess, these different methods will perform differently depending on the nature of the problem that you're trying to solve. There's no silver bullet solution that will fit all problems. With this in mind, we have built our Azure Quantum Optimization service to provide you with a selection of different solvers. The format you use to submit problems to the service remains the same, regardless of the type of solver you choose, giving you the flexibility to experiment, tune, and ultimately find the best fit to solve your optimization problems. All right, so now we know what we mean by optimization problems and cost functions. Let's explore how we go about solving these problems. The first step is, of course, to research, develop, and implement these optimization algorithms from scratch. Now, this obviously requires a high level of understanding of quantum or of optimization more generally, and a good deal of time investment without any guaranteed commercial benefit, as we can see here. Now, this is often considered a risky and expensive thing for a business to invest in, and probably not something that a lot of people want to really deeply specialize in. Fortunately, here at Microsoft, we spent time building out a team of optimization experts, so we do this part for you. This means that you get to reap the benefit of that algorithm's research without having to invest in it yourself. You can do this through one of two routes. You can either, when you engage with us through the paid for early access program, our team of optimization experts will work closely with you to build a solution tuned closely to your specific business problem. Examples of these collaborations include Case Western Reserve University, where we've helped to reduce the time taken for an MRI scan by 2/3. Risk modeling with the London-based financial firm Willis Towers Watson, and Ford, with whom we developed the traffic minimization case study that we were just exploring. Because we supply the optimization know-how in this scenario, the level of quantum understanding required from you is relatively reduced. The investment is relatively high, but this is balanced out by maximum commercial benefit as we build an algorithm to suit your specific business needs. The second route available to you is to make use of our suite of off-the-shelf solvers available through Azure Quantum. You may have seen these showcased through our partner collaborations, as Julie mentioned earlier. 1QBit, JIJ, and OTI Lumionics are all using our standard Azure Quantum Optimizer suite to solve their business problems. Now, these require a bare minimum of quantum understanding. All you need to know is how to represent your problem in a format that the solver can handle, and you're away. Because these are standardized solvers, you're unlikely to see the benefit of, say, a fully custom solver. However, the investment required is also much less significant. The optimizers are built through Azure like many other services which you may have used before. Now, with careful parameter tuning, you can still realize significant benefits by leveraging this suite of standard solvers. The bottom line here is that we believe that you should not need to be a quantum physicist to benefit from recent breakthroughs in optimization research. That's why, alongside our partners, we're developing and making available a wide range of these optimization algorithms through Azure Quantum. All right, it's now time to walk through the job shop scheduling problem and show you how you can use our suite of optimization tools in Azure Quantum to solve real-world problems today. I'm going to be walking through all of this pretty quickly as we don't have a lot of time today, but this will all be available on demand later if you do want to pause and work through anything. We'll also be releasing a detailed sample with walkthrough, as well as documentation covering all of this in more detail, so don't worry if you get a bit lost. I've also simplified the scenario a little so that I don't need to rush through it too much. Again, the full sample and problem walkthrough will be made available in the future so that you'll be able to see how it all comes together at your own speed later on. I will be using Jupyter notebooks for the demo, but you can of course use other familiar development environments such as VS Code or Visual Studio. We're also developing further samples to get you up and running with this as quickly as possible, so keep an eye out for those. In the job shop scheduling problem, we have a set of jobs, each of which has a specific processing time, and a set of machines, which we're using to perform these jobs. Each job is made up of a number of operations which must be completed in the correct order. The goal here is to complete all of the jobs in the shortest time possible. We'll explore this using an example. So imagine that we have a to-do list. Our list consists of 3 items, which we're going to call jobs. And these are to pay my electricity bill, to plan a camping trip, and to book a dentist appointment. Now, within each of these jobs, there is a number of operations that we need to perform before we can complete it. And each of those operations takes a specific amount of time and requires the use of a tool or a machine. At the bottom now, you can see the machines and the tools that we have available to us. So we have a laptop for logging into these websites. We've got a credit card for paying for these goods, a printer to print the receipts, and of course, good old tooth floss so we can guiltily floss before heading out to the dentist. We also have some constraints on how we can complete these jobs. The first one is that each of the operations in a job must take place in order. For example, you can't print the receipt before you've made a payment. This is called the precedence constraint. Secondly, each machine can only do one thing at a time. You couldn't, for example, simultaneously print 2 receipts unless you invest even in multiple printers. This is called the no overlap constraint. And lastly, you start a task or operation only once, and once started, you must complete it before you do anything else. We don't tolerate procrastination here. This is called the operation once constraint. Now, a valid solution to the job shop scheduling problem must satisfy all of these constraints. At this point, you might be asking, other than hyper-optimizing our to-do lists, why should we care about this problem? The answer is that job shop scheduling is a common and important problem in many industries. For example, in the automobile industry, manufacturing a car involves many different types of operations, which are performed by a number of specialized machines. Optimizing the production line to minimize manufacturing time can make for significant cost savings. This problem is a superset of the traveling salesman's problem, which we know is NP hard. All right, so I said that I'd be simplifying the problem for us to have enough time to explore this fully. And this is what I meant. What we're going to do is simply drop the no overlap constraint from the explanation. However, this will be included in the demo later. As I mentioned previously, you'll be able to check out the full detail of this through a sample in the future. So don't need to worry that you're missing out on anything. But the topics that I covered today should set you up to tackle the more complex version of the problem in the future. So anyway, how do we solve this? The first step is to take the constraints that we've identified here and formulate them as mathematical equations that we can then work with. Let's start by introducing some notation because I'm lazy and also because I want to avoid carpal tunnel syndrome. So we'll stick to our previous example of the to-do list. Here you can see that we've labeled our jobs as J and given them index numbers 0 to 2. to represent each of the 3 to-dos we had. We now define the operations that make up each job, represented by the letter O for obvious reasons. Now, to make this easier to code up later, we have chosen to identify all the operations with a continuous index number from 0 all the way through to 9, rather than, for example, starting from 0 for each job. This allows us to keep track of operations by this ID number in the code and schedule them according to our constraints and machine availability. We can then tie the operations back to their jobs later on using a reference table. And here you see the jobs defined mathematically using this new notation. So for example, here we have job 0, and it consists of operations 0, 1, and 2 as defined here. Great, so the next piece of notation that we're going to need is a binary variable, which we're going to call xit. I meaning the operation number and t meaning the time. So this variable is equal to 1 if operation I starts at time t and is equal to 0 at all other times. Now, this binary variable makes this a binary optimization. More generally, this is something that's called a polynomial unconstrained binary optimization, or PUBO problem. The polynomial part just means that we can have higher order polynomials, such as cubed or to the 4th and higher. We'll see some of those terms later. So the next thing we'll define is PI, which is the processing time for operation I, i.e. the amount of time it takes operation I to complete, to finish running. So for example, if we had operation I starting at time t, it would finish at time t plus pi. Similarly, if we had operation I plus 1 starting at time s, this would finish at time s plus pi plus 1, which is the processing time for operation I plus 1. I'll give an example in a minute to kind of avoid confusion. Now, t, as you might have guessed, represents our simulation time. This goes from time 0 through to big T here in integer steps. So big T is the longest that we're happy for the whole set of jobs to take overall, i.e. our max simulation time. So back to our constraints. How do we start to formulate this? So we want to be able to represent these constraints mathematically before we can code it up. We're going to do this using a penalty model. Basically, every time our optimizer suggests a solution that violates one or more constraints, we need to give that solution a penalty. For the precedence constraint, we want to assign a penalty whenever operation I plus 1 starts before operation I has finished, i.e. they start out of order. For the operation once constraint, we want to assign a penalty if a job is scheduled more than once during the simulation, or if it's not scheduled at all during the simulation. We'll now explore how to formulate these constraints in a form that will enable us to represent them as code. We'll start with the precedence constraint. And we'll use O3 and O4 as an example. So that's picking our campsite and paying online for it. So what we want to do is add a penalty if operation 4 starts before operation 3 finishes. So what we do is we say that operation 3 here can start at any time from t equals 0 all the way to big T. So we're going to say big T equals 3 in this case. And that means that t plus p3, which is the ending time of operation 3, will be this plus 2, because we've defined p3 to be 2 here. So these are the ending times for the possible ending times for our operation 3. So we've written down here the possible ending time, some possible ending times for operation, or starting times, sorry, for operation 4. In order to not violate this constraint, the start time of operation 4, S, needs to be bigger than or equal to the ending time of operation 3. So if operation 3 started at time 0, operation 4, could start at time 2, 3, or 4. And likewise, as we go down the table here. On the other hand, if the starting time of operation 3 happens to be less than the ending time of operation, sorry, the starting time of operation 4 is less than the ending time of operation 3, we violated the constraint. And these are some examples of time values that would violate the constraint. So how does that look mathematically, more generally? So firstly, what we want to do here is we want to sum over all of the operations in a particular job. So let's say this is operation 3, or sorry, this is job 1 here. So we want to sum over operations 3, 4, and 5. The next thing that we do is we sum for all of the times that violate that constraint. So these times in this column. So these give us limits for a nested for loop. So for this loop, we're going to take from time equals 0 all the way to our maximum simulation time of t. And here we're going to go from s is 0 all the way to s is less than t plus pi, because those are the times that will violate that constraint. So that for loop will look something along the lines of this. So we say for operation in job for time equals 0 all the way through to time equals t, while s is less, oh dear, sorry, is less than, oh, sorry about this, there we go, is less than t plus pi, we penalize. I will show this in code and not my horrible scroll slightly later on. But this is the kind of idea. So we're building this nested for loop to add penalties whenever we violate this constraint. All right, one constraint down, one to go. This time we have the operation once constraint. Now, according to this constraint, so sorry, if we remember back to the beginning that we have this x variable, and that equals 1 if the job starts at time t, and 0 otherwise, right? So what we're saying here is that across the entire simulation time, the x values for an operation across all of those times should only ever be 1 once, right? It should only start once, which means that this sum here should only ever equal 1. In this instance, we see that we've got 2 lots of x being 1. Now this is a problem because that means that that operation 3 here has started both at time 1 and at time 2, which violates our constraint. It means that our sum is bigger than 1, and therefore we should add a penalty. In this last example, you'll notice that there is no instance where x for operation 3 equals 1. That means that this operation is never scheduled, which is also in violation. And our sum is again not equal to 1. So generally, this is how this looks. So this just maps back to our sum here, so this column or row. So we want this to always equal 0, or sorry, always equal 1, because that means it's been scheduled once and only once during the entire time that we've had for the simulation. Now, if this equals 1, and we take away 1 from it here, if we don't violate the constraint, this should always end up being 0, which means that there's no penalty added. So let's take the instance where it's been scheduled more than once. So instead of this equaling 1, it's now bigger than 1. Now we have a number that's bigger than 1, and we're taking 1 away from it. So the sum, or this entire term here, is going to be greater than 0, which means that there's going to be a penalty added. Lastly, we have the case where this equals 0, as in we've never scheduled operation 3, which is also a problem. In this case, we get 0 minus 1, which obviously equals minus 1. Oops. But we need to ensure that this penalty is always positive, because otherwise we'd be reducing the penalty, which makes no sense. So what we do is we square it, because of course minus 1 squared equals 1, and now we have a positive penalty value. And then what we do here with this sum is we just sum across all of the operations and the jobs. So that's all very nice, but we're going to need the expanded version of this when we actually go to write this up in code form. So for this particular example, again, we're going to take good old operation 3. And we're going to define that the full simulation time is 2, so we can have t values of 0 and 1. So the first thing I'm going to do is simply substitute t equals 0 and 1 for t there, like so. And because I'm really lazy and I just cannot be bothered writing these out multiple times, we're going to just sub in x and y. So x equals this one and y equals that. Pretty straightforward. Next thing we need to do is expand out these brackets. So we get, oops, we get this. And lastly, we multiply everything in this bracket with everything in the next bracket as so, to get our final expanded quadratic equation. Now, of course, if we had more t values, this would be a higher order polynomial, because you'd get x, y, and z, or x, y, z, a, b, c, however many time intervals we have. In this particular case, the highest order of the polynomial is going to be quadratic, or to the power of 2. But as I say, this could be higher in general. All right, so now we have both of our constraints. This is good. How do we combine them? How do we actually form a cost function from these constraint functions? Turns out to be simpler than you might think. All we do is we multiply them by a weight factor, or a coefficient, so alpha, beta, and gamma here, and then we add them together. You'll notice here that I've added back our no overlap constraint, because without that we wouldn't be getting feasible solutions in our code. But you can see that in the sample later. Don't worry too much about it. Okay, on to the code. Excellent. All right, as I said earlier, I'm going to be showing you this in a Jupyter notebook. The Azure Quantum service is still in preview, so I've queued up some results that I ran earlier, and also because my bandwidth tends to be a bit dubious sometimes. So let's get started. So first things first, the code that we're going to see now is going to take those constraints that we just built out, and it's going to transform them into something that looks like this piece here. Now, these are called terms insofar as our optimization SDK is concerned. The C part here represents the coefficient of that term. So that's the weights, alpha, beta, and gamma that we were talking about a second ago. And the indices represent our X, I, T terms, those binary variables. So these tell us which configurations need to be penalized. Now, to simplify this demo, I've just assumed that all the jobs have an equal number of operations. Some pretty straightforward setup stuff first, some includes. Most important thing to note here is that we're getting the term structure from Azure Quantum optimization. So our first constraint, precedence. This should be familiar by now. So for each job, we do this sum, right? So this is a sum over all the operations in that job for all of the times that violate this constraint. And this is what the code looks like, simpler than you might have thought. So this is the for loop that I wrote out in on the slides. So we're looping through all of the jobs and all the operations in that job. Then we loop from time 0 to big T, so until the end of the simulation. And then we add penalty terms here to the cost function over any time that violates our constraint. So any time for S that's smaller than T plus PI, the running time of the previous operation. The next thing that we have, the operation once constraint. So this is what we just expanded. This should look familiar as well. So we're going to take this expanded equation and we're going to turn it into code. So what we're doing here again is looping through all of our jobs and all of our operations. Then we take a loop through the whole of the simulation. And here we add our terms. So for the squared terms, we're going to have two lots of indices because they're squared. And the coefficient here, so there's nothing multiplying x or y in the front. There's no 3 or 4 or whatever it is. Our coefficient just remains times by 1. The next term has these -2 factors in front of each of them. So we times this by -2. And it's not y squared or x squared. It's just to the power 1. So we get this index. Lastly, or not lastly, but next we have our +2xy term. So in this case, we're going to loop over all the other start times because these are the cross terms. We're going to multiply by our coefficient by 2 to make sure that we take this into account. And then we have the two indices of the two jobs, of the two operations, I'm sorry. And then we append our last +1 term. The next thing we do is actually generate those terms using those functions that we have already defined. So we have our weights here, alpha, beta, and gamma. And we call our 3 constraint functions. And then we just add them together. So we're creating this is how we create our cost function. Lastly, we set our problem parameters. So in this particular instance, we've chosen to have 2 jobs with 2 operations per job. That makes 4 operations total. We have 2 machines overall. In this case, we've chosen to have the processing time be 1 time unit for each of those operations. And the time overall for the simulation will be 4. This is mostly so we can visualize the results more easily when they're run. Now, this little matrix here simply maps the operations running in each job to the particular machine that it's going to target or that it needs to complete. So now that we've built up our penalty terms, we need to learn how to submit the problem to the Azure Quantum service. First thing we need to do is to create a workspace. Mike already showed us how to do this through the Azure portal. And this is where you would call all of that, or where you would enter all of that information. You then call workspace.login, and it should hopefully give you this to show that you have authenticated successfully. The next thing we do is submit the problem to the solver. Now, this shows us synchronously submitting the problem to the solver. In this case, we've chosen to use the simulated annealing solver, but you could swap in any of the other solver types available through Azure Quantum and keep the same problem format. It's definitely worth experimenting to see which solver performs best for your problem. This is where we submit the problem to the service with solver.optimize. And then we read out the configuration that's returned. So the output will be, so these dots are just as it's running, and then here's the configuration that was returned. Back to that in a minute. We can, of course, also run these jobs asynchronously. So in this case, you use solver.submit rather than optimize. And then you can refresh to get the status of your job. So in this case, it happened to be waiting when I ran it. You can go from waiting, executing, finished, succeeded, as you might expect. And again, we've printed out the configuration that was returned. Now that we've got the configuration back from the solver, we need to map this configuration back to our understanding of the problem so we can understand the results. So this is what we are doing here. First of all, we produce a one-dimensional array from the dictionary that you saw, the config returned by the solver. So this here, it holds all of our XIT values for all of our operations over the full simulation time. We then split this into a matrix representation and print it out for easy viewing, as you can see here. So we have time across the top. We have our X values along the axis here, and these are our X values. So 1 if the operation starts at that time, and it's 0 otherwise. Now, the sharp-eyed among you may have noticed that, in fact, this job was never scheduled. So actually, this run has failed. This is an important thing to know. So just creating a problem definition and submitting it to a solver is not all the work that we have to do here. For one, there are many ways in which we can represent our problem in terms. So we need to experiment to find the best representation. The other thing that we need to tune is the coefficients, those weights, alpha, beta, and gamma. Getting those quite right is an art form in and of itself. Now the bottom line here shows our parsed output. So I've added some kind of just labels here. So this first array represents job 0, so the 2 operations within job 0. The first one, or operation 0, is scheduled for time 1. And this -1 means that we haven't been able to schedule the second operation of job 0. Likewise, times 2 and 3 here for jobs 1. And here now you can see an example of a configuration that does satisfy all our constraints. You can see that there is one instance where X is 1 across all 4 operations, and a nice diagonal here. And you can see here that job operation 0 is scheduled for time 0, 1 for 1, etc. So that ends the code section. All right, so you've now seen how we can go about representing a particular industry problem in terms of a PUBO and solve it using an Azure Quantum optimizer. It's been a bit of a whirlwind tour, I know, but hopefully you understand a little better now how you would actually go about constructing these problems. So all the way from a kind of simplified real world problem through to building out our constraints, our terms, and then mapping those to code, and then tweaking, tuning our parameters and our cost function to get the best out of the optimization service. Now you can always, as I said, come back and rewatch this later on or make use of the sample once it has been published. To kickstart your creative thinking, I've included some extra examples of industry applications on this slide. I know that I and the rest of the team really look forward to seeing what problems you will all solve using Azure Quantum in the future. As far as next steps are concerned, please do head over to azure.com/quantum if you haven't already signed up for access to the private preview. You can learn more at our documentation site, which is also linked there. And lastly, you can check out more code, samples, and contribute to this community effort if you head over to our Quantum GitHub repo. Thank you so much for your time today. I'll now hand back over to Matt, who will introduce the next session.
Anita, thank you. That was a fantastic session. And I think everyone needs to pat themselves on the back a bit. You've made it through the morning session, so congratulations for that. We've been doing our best to answer questions in the chat. Really appreciate the rich dialogue going on over there, and we'll continue to answer questions. One thing that has come up time and time again, and I'm glad Anita just recapped it, is there is a limited preview available today for Azure Quantum. So please follow the links being provided to sign up for that. And stay tuned throughout the rest of this year as we make additional progress on opening up more access to Azure Quantum. With that being said, let's go ahead and end right on time. Anita, fantastic job. With us ready for a big break now. And we encourage people to come back at 12 noon Pacific time and be able to join us for the second half. So you should have a separate logon link, join link for the second half of today called part 2. And that will commence promptly at 12 o'clock Pacific time, where we will jump right back in and explore another exciting solution area around how to use Q# to actually program algorithms and push those jobs for quantum execution. So again, thanks everyone for joining the first part. Please go get a bite to eat, get a refresher, stretch a bit, and we'll see you back here at 12 noon Pacific. Thank you.
Great. Thanks, Matt. And just to add to that, we have posted a link for the part 2 session. You can find that in the Q&A now. You will also be receiving an email with that direct link as well. So watch for that. If you can't find your way in, you can always hit that registration page again, re-register, and join that way as well. So this will conclude part 1. You may now disconnect. Welcome to part 2 of today's event, Azure Quantum Developer Workshop. This broadcast is being recorded on behalf of the Microsoft Corporation. If you do not consent to being part of a recorded session, please disconnect your line at this time. The recording will be available at the same location you joined today's event. To learn more about the ways you can participate, please click the Q&A button in the lower right corner of your screen. We encourage you to interact by using the Q&A tool at any time to ask questions regarding content or to request support. Your feedback is important. Please take a few minutes to complete a survey that will appear as an announcement at the end of the broadcast. We thank you in advance for your support. If you experience any technical difficulties, please first refresh your browser. If this does not resolve your issue, please send a message and we'll be happy to help you through the chat. Now I'd like to hand things over to your first presenter. Matt, you have the floor.
All right, thank you very much. So welcome back everyone who joined us for this morning session. Hopefully you're able to get a few minutes to refresh and maybe a bite to eat, catch up on some work. For those that may be joining new, I'm Matt Zanner. I'll be your host today, taking us through a great set of content that myself and colleagues have prepared for you to help share our journey towards a scalable future for quantum. Let me go ahead and share with you that agenda for the remainder of our afternoon. If you can look here on your screen, this is the same sort of map that we'll be using throughout the day to help orient you where we're at and what's ahead. In just a few minutes, I'll be turning it over to Megan to jump in on one of the other key solution areas for Azure Quantum, and that's using Q# to actually write quantum algorithms and be able to actually throw jobs towards quantum execution up on the platform, so quantum hardware execution. After that, we will have a good chunk of time dedicated to a virtual lab. So this will be sort of hands-on in nature. You'll be able to follow along in your own environments as much as you want. And that'll be a really good opportunity to get hands-on exposure to some of the tooling that we've shared so far and how it can be applied to the various topics we've been discussing. We'll then start to pull back just a little bit towards later in the afternoon and share with you all the great assets and resources that we have to help you along a potential path in quantum computing. And we'll close the day with the last session really hopefully being a highlight for you, where we can make personal what it means to build a quantum community, right? And share some actual examples of people contributing in various ways to further the objectives for all of us along this journey. So with that, let me go ahead and turn it over to Megan, and it is yours, Megan, to take away. Thanks.
Thanks, Matt. Sorry, had a couple technical difficulties there. Hi, everybody. Welcome to the afternoon session of the Azure Quantum Developer Workshop. And I'm super excited to walk you all through today a deeper dive into Q# and quantum execution. So I'm Megan Brown. I am a program manager working in the quantum systems team at Microsoft Quantum. And my main focus areas are on quantum execution, Q#, the quantum development kit, and specifically around the end-to-end developer experience. So what does it look like to write a Q# application, to submit that job to Azure Quantum, and being able to really develop algorithms for quantum computers. So today we're going to go into a little bit more detail what is Azure quantum execution, a little bit of a refresher from the morning session for those of you who are able to attend that, just kind of giving you some more detail on what do we mean when we say quantum execution. In addition, we'll be looking in more detail at the quantum development kit, some of the different components of the quantum development kit, and then really looking at why Q#. Why do we have this new programming language? Why was it important to develop a quantum programming language? Then we'll get into a little bit more detail of some of the components of the quantum development kit, specifically around our libraries and tools. And there's a demo at the end of the presentation to just show you how all of these things come together and what that end-to-end flow looks like. Azure Quantum applications fall into two categories: quantum optimization and quantum execution. Quantum optimization enables you to solve difficult optimization problems on classical hardware that are inspired by physical processes. So to take advantage of quantum optimization in Azure Quantum, you would use our off-the-shelf quantum optimization solvers. And this is where you have a specific problem and you're bringing your problem to an algorithm in Azure Quantum that you can then apply to solving that problem. But today, I'm going to be focusing in on quantum execution. Quantum execution is focused on developing quantum algorithms that are designed to run on quantum hardware. And these are algorithms that use the power of quantum mechanics. Applications for quantum execution are developed in Q# and can be run on quantum hardware and simulators using Azure Quantum and the Quantum Development Kit. The Quantum Development Kit contains all the tools needed to develop applications for Azure Quantum, both on the quantum optimization side and on the quantum execution side. So again, today we're going to focus in really on Q# and quantum execution. So Q# is part of the Quantum Development Kit, and it's a programming language designed specifically for building quantum applications. The Quantum Development Kit, or QDK, also includes a variety of tools to make it easy to get started with quantum application development and quantum execution, including the Quantum Katas tutorials, Microsoft Learn modules, examples, and Kitty will go into a little bit more detail on some of these later in our learning session. So I highly encourage you to stick around to dive deeper into some of these learning tools. In addition, we have IDE integration for Visual Studio Code, and Jupyter Notebooks, as well as a selection of Q# libraries. And this is spanning from standard functionality focused on making it easier to develop to really domain-specific libraries focused on specific industries and specific problem areas within quantum. We also offer quantum simulators and resource estimators as part of the Quantum Development Kit to help you create, test, and run applications. We'll go deeper into some of these tools later in the session. But first, I want to take a step back and really focus in on why Q#, why we have this programming language, and why this programming language is important and will make your lives easier as quantum developers. Q# was designed specifically for developing quantum applications for quantum computers. The nature of quantum computers is built directly into the language and then enhanced with library functionality and high-level language features that are specific to quantum application development. So a specific example of this is a qubit. So you have physical qubits on your actual quantum computer, but in developing an algorithm, you want to manipulate logical qubits without having to worry about the various layers to map a logical qubit down to a physical qubit. So in Q#, a qubit is actually a data type. So you don't have to worry about those different layers. It's all abstracted for you to develop an algorithm focused on those logical qubits. We also have quantum concepts like superposition, entanglement, and measurement that can all be modeled through implicit side effects in Q#. You can really think of Q# programs as classical programs that can send quantum instructions to a quantum device. And this quantum device is really an accelerator for your classical workload. Having been designed specifically with quantum execution workflows in mind, Q# enables the automation of many of these classical tasks that are needed to make good use of quantum computers. So a specific example, again, would be inverting a sequence of instructions, which is something that's fairly common in quantum application development. Q# has the within functionality, and this helps automate that set of classical instructions that you would need to do in order to make sure that sort of your operation is invertible, your sequence of instructions is invertible. So this really lets you focus on the algorithm you want to develop and abstracts away from those classical pieces that you would otherwise have to do manually. So these design choices really help you create applications that are optimized for execution on quantum computers by, like I said, abstracting out some of these manual tasks that are required to go from a classical program to a quantum program. Now we've optimized for this conversion from classical tasks to quantum tasks, but we also are optimizing for quantum computers on different architectures. So today, if you're developing a classical software program, unless you're developing really at the systems level or at kind of a low-level program, you generally don't want to worry too much or think too much about that underlying hardware that you're running on. And Q# provides the same level of hardware abstraction for quantum development. You don't have to worry about what specific type of qubits or what specific chip architecture of the quantum device you're running on. You can just focus on developing that algorithm and solving the problems that you want to solve. In addition, developing an application with Q# means that you'll be able to run that application on a variety of quantum execution targets in Azure. So not only is Q# designed with this principle in mind, we're giving you the actual ability to execute on that through Azure Quantum by providing access through our partners to different types of hardware and software. Now, as this hardware scales, so can your Q# applications. So you can start developing a Q# application today, run it on the hardware through Azure Quantum, and then be pretty confident that that application can scale and would be able to run on scalable quantum hardware in the future. In addition to this hardware scale, Q# is also very focused on the scalability of development. It's a high-level programming language, really specifically designed for creating quantum algorithms. And it's also designed to be really familiar to classical programming languages that you already know, and to make it easier to learn and easier to express those algorithms by using familiar concepts. The high-level language abstractions, Q# libraries, and the ability to easily share and collaborate on code enables greater scalability of development and applications. As quantum computers evolve and scale, so will the complexity of the applications that we can and will execute on them. And this will probably require using quantum algorithms from our classical applications. So you might have an existing classical application in your organization and want to send out specific instructions to a quantum device for a specific workflow that is optimized for a quantum computer. And we've built in this functionality today by including interoperability with classical programming languages and frameworks like Python and .NET. So you can call into a Q# operation from your Python or .NET applications. In creating Q#, it's also been really important to support great developer tools that are already on the market and really integrate with the developer tools that you all use today. And that's why we've integrated through extensions with Visual Studio, Visual Studio Code, and Visual Studio Code Spaces, which was announced at Ignite last year, as well as Jupyter Notebooks. And these integrations take advantage of some of the great features that you're used to in these environments. So in the Visual Studio Code, that includes IntelliSense for features such as code completion and code actions. So now let's talk a little bit about some of the libraries and tools and get into a little more of the nitty-gritty of those components of the Quantum Development Kit. So I mentioned a few times that the QDK includes some great Q# libraries to make it easier for you to develop quantum applications. So let's take a look at what some of those are. Firstly, we have the standard library, and this is probably going to be your best friend in your Q# development process because this is really where the foundational building blocks are included. So this contains type conversions, control flow, your data structures and models, all those things that you're likely to need when you're trying to develop a high-level algorithm in Q#. We also have the numerics library, which provides support for integer arithmetic, including support for quantum integers. Then we get into our increasingly domain-specific libraries. The first one of these is our quantum chemistry library, which introduces a simulation of physical systems. This library was co-developed with the Pacific Northwest National Laboratory with the goal of creating Q# applications for quantum chemistry. It uses the Broom-Bridge open standard to describe electronic structure problems for quantum chemistry. Quantum machine learning is the newest addition to our collection of great libraries and provides an introduction to early quantum machine learning using circuit-centric quantum classifiers. So now let's talk about simulation and resource estimation, and specifically how that fits into your end-to-end developer process for quantum execution. So in addition to offering access to quantum hardware through Azure Quantum and our partners, the Quantum Development Kit includes software simulators to help you validate your program prior to submitting your job to Azure Quantum. And this also means that that you can run slightly more complex applications than you can run on hardware today by using the simulator that's packaged in with the Quantum Development Kit. Now, the next question might be, how do you know if your quantum application is too complex to run on hardware today? Or how do you know what to optimize in your application's architecture to make those changes that you need in order to run it on hardware or in order to fit some specific target that you're looking for in your process? And that's where the resource estimator comes in. So it's a little bit self-explanatory. The resource estimator provides estimates on the resources required to run a given Q# program. And what I mean by resources are quantum resources. So this could be the number of various types of gates, number of measurements, qubit rotations, the depth of your quantum circuit, and more. So resource estimation for quantum execution enables you to create Q# applications and understand how they'll run without needing to wait for scalable hardware to become available or without needing to run it on hardware at all. So these tools help you refine your applications and explore quantum application development, as well as develop applications for future hardware with an understanding of what kind of resources are required to execute it. So now let's see how this all comes together. So I recorded a demo for you all earlier this week. So I'm going to play that now, and we'll go through some of the different pieces, how all these things come together in the developer workflow, and run a Q# application on Azure Quantum. So here I have a basic Q# application that I've created after installing the Quantum Development Kit Visual Studio Code extension. And creating this project was really easy. Once you have the extension for Visual Studio Code, you just open the command palette. And when you have the extension, you'll see these two Q# commands populated. So the first we have create new project, and really the second one, install project template. You want to do this shortly after installing, before going and creating a new project, because what this will do is it'll give you access to this kind of default project. And going forward with Azure Quantum, we're actually going to have project templates for the specific execution targets that you might want to develop an application for. So highly recommend installing the project templates, just making your development process a little bit easier. So to create this project, I installed the project templates, and then I just created a new Q# project, and that creates this default Hello World application. So if I were to run this, I would just get a little console message saying, hello, Quantum World, your typical Hello World program. But let's look at doing something a little bit more interesting. So I'm just going to replace the Hello World example with our quantum random number generator. You're going to get a little bit more information on the quantum random number generator in the virtual lab. So I highly recommend you stick around and attend that and get a little bit more detail. I'm going to go over, just some highlights of what this code is doing, and really trying to reiterate some of the concepts that we talked about earlier in why do we have Q#, what our libraries and other tooling provides for you in the developer experience. So here we can see we've included a few libraries, and these are all kind of part of the standard library functionality. So these are things that you'll probably use very, very frequently. And this gives us access to the qubit data type, like I was mentioning earlier, and empowering us to not worry so much about the physical qubit representation or the architecture of a physical qubit or a physical device, and really focus on how do we logically want to manipulate qubits in our application? What do we need to do to qubits to move our algorithm forward or get the result that we want to get at the end? And this is also facilitated with the using function. So this provides just a little bit of an easier way for us to kind of allocate and deallocate resources. And here we have a Hadamard gate or an H gate. Again, you'll get a little bit more information on specifically what some of these things do in the virtual lab. But essentially, this puts a qubit into superposition, meaning that it has either a 50% chance of being measured as a 0 or a 50% chance of being measured as a 1. So that's all we're doing is we're taking this qubit that was in some base state and saying, put it into this state where it could, has an equal probability of being a 0 or a 1. Now, once we've done that, we want to measure that qubit because that's where we're going to get our random result back. And that randomness comes from that 50% probability. Is it a 0 or is it a 1? And that's where this mResetZ operation comes in. And what this actually kind of collapses a few of those manual tasks down into a single line of code. And this is where some of the power of our libraries comes in and some of that ease of development comes in. This is a few different operations that are simplified by use of our libraries. So the first thing that happens in this operation is we do a measurement of the qubit to get back that result. Do we get back a 0? Do we get back a 1? And then we're going and resetting the qubit by doing a Z gate on the qubit. So let's just see what this looks like running on our local simulator. So as I mentioned, the Quantum Development Kit comes with local simulation tools, and this is what will run on by default. And this is all happening on your local machine using the processing power on your local device to do that simulation. And here we see we got back a 1. And if we were to run this again, we might get back a different result. We might get back a 0, we might get back another 1. And it's random. So this is where we can build our random number. Now we just ran this locally using the local simulator. Now let's talk a little bit of how you would run this on Azure Quantum, how you would set, what is that target device that you actually want to run this on, and what does that look like? So over here in the project file, I've added this execution target parameter. And this essentially sets what target device is this application designed for. And one of the great things about these, this actually tells the compiler what device you are optimizing your application for. And this is really where the power of the design time feedback and the power of our simulator comes in, because it lets you manipulate your application, run your application, make changes prior to submitting to Azure, so that when you're submitting your quantum execution program to Azure, you can be pretty confident that your algorithm is going to do what you want it to do, and is actually going to be able to run on that target device. And you might find that sometimes you might get errors that your program is using too many resources or isn't able to run. And one of the ways that you can to mitigate this is using the resource estimation tool that I mentioned earlier. And this is really easy to run as well, and it's pretty separate from that execution target. So they're decoupled, so that regardless of what application what device you're targeting with your quantum application, you can run your resource estimator, and it will tell you in general what types of resources your application will be consuming. So if we go and run this, we'll get back a result that shows us these different types of operations, of gates, of resources that your program would use. And here's where you can kind of optimize. So you can look at your algorithm, and depending on the type of device you're targeting, or what resources you have access to, you might want to optimize for one of these over the other. And this tool provides a deep understanding and a view of what resources are my application consuming too much of to be able to run my algorithm efficiently on the type of hardware or the type of software that I want to target. So using the simulators and the execution target functionality and the resource estimator can really help you develop a deep intuition for what your application is doing and how it will run, both on hardware today and on hardware tomorrow. And that's another great thing about the resource estimator is, this can help you optimize an algorithm before even having access to the hardware that would run that algorithm. So you can start solving problems today. You can start developing in Q# today and start, understanding how those problems would be solved using Q#, all using the resource estimation tools that you have access to right now. So now let's get into actually submitting a job to Azure Quantum. So like I said, over here, I'm targeting the IonQ's device. So this is the IonQ PU, their quantum processing unit. This is one of the hardware devices that we have access to through Azure Quantum. I've already provisioned the resources through the Azure portal. If you're interested in how to do that, I would go back and check the recording of the Azure Quantum overview session that happened earlier today. That should have all the information that you need to understand the end-to-end process for provisioning resources in the Azure portal. But for now, I've already done all of that. So I'm just going to go back over here, and I'm going to submit my job. And so here again, I'm specifying where I want my job to execute. I'm giving my job a name, just a few more human readable names that I can go back and track with. This is an optional parameter. You don't need to include it. You'll get a unique job ID after submitting to Azure, which we'll see in a second. And I have this is formatting for the table for the output to just make it a little bit easier to read. So here I'm going to submit that. And submit is an asynchronous functionality for our Azure Quantum command line interface. So this will submit the job to Azure Quantum, return a job ID that we'll see in a second, and using that job ID or the job name that I gave, I can go and query the results later. So submit isn't going to automatically give me back the results. I would need to go and look for that job output using a separate command later. And so here we see we get back the job ID, we see the name that I submitted it as, we have the status of waiting, so it means that the my application is sort of queued for execution on the service for the target device, and we just see what the target is and what the submission time is. So I could use this job ID to then query the status and get updates on this, kind of however often I want to, or I could write a script to go and do that for me. And we also offer the execute functionality, which does that polling until we get the result back. So here I'm going to switch it up a little bit. I'm going to show you what this looks like running on the IonQ simulator. Everything else is basically the same as submit, except we're going to do that synchronous version of submit using the execute command, and we're going to submit it to the IonQ simulator. So here we're going to see it's going to take a second longer because we're actually going, we're not just queuing a job, we are going to be getting, waiting for that job to execute, retrieving the result back from that operation. Here we go. So now we have this result back, and you can really see the probabilistic nature of these algorithms in the results that you get back from hardware and from the hardware simulators. So what this is essentially showing is that 50% probability that I mentioned earlier. So by putting the qubit into superposition, we have a 50% chance of it being a 0, 50% chance of it being 1, and we're actually seeing that reflected in the results here. All right, hopefully that's I'll give you a great kind of sneak behind the curtain to see what some of these tools look like and some insight into what it looks like to run quantum execution applications on Azure Quantum. One of the great things is that actually most of what was part of that demo is available for you today. So you can go and get started with the Quantum Development Kit and Q# using the link on this slide, and that will give you access to the simulation tools, to Q#, to all of the library functionality, as well as resource estimation. Then you can sign up for Azure Quantum Early Access. We're going into public preview later in the year, so be sure to sign up for that to get notified of any updates and to be some of the first folks to try out some of that great quantum execution functionality that we're working on. And again, in order to help you kind of get started with Q#, with quantum development, highly recommend checking out our Microsoft Learn modules, as well as the quantum katas. And you'll have more detail on those in the learning session later today. I also highly encourage you to stick around for some hands-on work on the virtual lab with Maria and Ryan. This will go a lot deeper into some of what I explored in the demo and some of the concepts that we touched on earlier in the session. So definitely recommend sticking around for that. And I think it's also going to be using our Jupyter Notebooks experience, which is a great highlight. So with that, thank you all for listening to me talk about Q# and quantum execution. I hope you're excited to get started. Back to you, Matt.
Thanks, Megan. Great session. If you don't mind kicking your slide ahead just once, that'd be great. Appreciate it. So as Megan mentioned, we've got some great content coming up with the virtual lab, where Maria and Ryan will take us through some actual algorithm examples. And Megan, would be awesome if you could take a peek at some of the questions that came in on the queue. The wizards behind the curtain are frantically trying to respond to everyone's questions. We certainly appreciate the dialogue over there, and we'll continue to provide responses. So please be patient, and we're working through them. With that, I'd love to go ahead and turn it over now to Maria and Ryan. Both of you, please take it away.
Hello, everybody. Thank you for the introduction, Matt. My name is Maria, and I will be with you for the next hour and a half to walk you through the basics of quantum computing and using Q# for solving simple problems and implementing simple algorithms. Let's go. So a quick overview of this session. We will start with an introduction to quantum computing. I'm not assuming that people on this call are familiar with the basics, so it's always good to get a refresher. The only thing you're going to need as a prerequisite is matrix multiplication, 2 by 2 matrices, nothing larger than that, I promise. Then we will do a simple hands-on exercise implementing random number generation. After this, we will look at a slightly more complicated algorithm. It is not an algorithm of practical value, but it has interest because it is the simplest algorithm that allows us to demonstrate the quantum speedup, the place from which the power of quantum computing is coming. Then we will do a second hands-on section implementing this algorithm, and then I will hand it over to Ryan to show you how to run those same quantum programs we have written in the first section on Azure Quantum. It is a little tricky to do a proper hands-on exercise in presentation mode. So what we're going to do is I'm going to show you how to get started. Then I will take a couple minutes break to allow you to try and solve the tasks yourself. We will unfortunately not have the bandwidth to help everybody to go through the tasks, but I will show you the solutions and comment on them before I move on to the next section. Also, all the materials used in this lab are going to be available online after the session. Well, they're already available. So you will be able to return to them at your own pace and take your time with them. What are we going to learn today? We are going to take a little recap of the linear algebra involved, cover the basic concepts of quantum computing. We will cover only as much as we need to talk about our algorithms that we want to implement, because quantum computing is a vast topic and it's not going to be possible to explain all of it in an hour and a half. We will talk about a very fundamental concept of quantum oracles, which we use as one of the ways to define quantum speedup. And of course, we will talk a lot about implementing algorithms in Q#, the way mathematical concepts are reflected in the programming language, and how to run it on Azure Quantum. Our first step is basic concepts of quantum computing. The most basic concept is, of course, the unit of computation. In classical computing, our smallest piece of information, our unit of computation, is bit. A bit has a state. It's a very simple state. It's just a number, 0 or 1. In quantum computing, our units of computations are qubits, short for quantum bits. Their states are vectors. And this is where it gets interesting. We have quantum states that mimic the classical values 0 and 1. As a corollary of this, we can simulate any classical computation on a quantum computer. It's just that we don't have a reason to do this. We want to do purely quantum things on a quantum computer because that's where it's powerful at. So those states that mimic 0 and 1 are called basis states. They are column vectors of length 2. So the 0 state is a column vector in which the first element is 1 and the second is 0. And the 1 equivalent is the other way around. The first element is 0 and the second one is 1. The notation you see here, kind of 0 and 1 enclosed in a vertical bar and an angle, is called cat notation. It is basically to denote that we are doing something quantum and not just discussing vectors. You can go without it. It's going to be much more useful if we talk about multi-qubit systems, but today we're not going to talk about them. So for now, think of it as just variable names. So it's a quantum variable 0 and quantum variable 1. The states that don't have a classical equivalent are called superposition states. Those are column vector states in which both elements of the vector, the first and the second one, are not 0. We say that superposition states are linear combinations of basis states. If you remember the basics of linear algebra, you will remember that vectors are linear, so you can multiply them by a scalar number, you can add them, and it's the same as multiplying each element of the vector by a number and adding up vectors element-wise. This is actually the first lesson of today's session, if you don't know this yet. We never say that superposition state means that a qubit is in 0 and 1 state simultaneously. This is just not correct. A qubit is in a specific state that is a certain linear combination of 0 and 1 states. And there is a plethora of such states. It's also not correct to say that there is just one superposition state. Superposition states are all states that are not basis states. There are a lot of them. Now, the coefficients of superposition states can in general be complex numbers, but for the algorithms I'm going to discuss today, we don't actually need complex numbers. We are going to stick to just real numbers. And here is how you can visualize quantum states. The vectors that represent quantum states have to be normalized, which is to say that the sum of absolute values of the components squared has to be 1. Geometrically, this means that these two numbers have to belong to a unit circle. So here we see that the 0 state, the state in which the first component is 1 and the second is 0, is on the horizontal axis. The 1 state is on the vertical axis, and any point on the circle corresponds to some superposition state. For example, this point corresponds to a state in which 0 and 1 state have equal amplitudes. And since they have to be normalized, you know that these amplitudes are going to be 1 over square root of 2. We are going to use this visualization later today when we discuss quantum gates. Now, how do we represent qubits in Q#? It is one of the topics that people often have questions about, so let me spend a moment discussing this in slightly more details. So the mathematical notation of qubits describes qubit states. So in the previous slides, I was mostly focusing on the vectors that represent qubit states. But this is not actually what is happening in a physical system. Remember that quantum computing has to reflect the behavior of quantum systems. It is slightly abstracted behavior, but still we wanted to reflect things that we can actually do with our physical systems. And we want our programming tools to reflect those same capabilities. It would be extremely inconvenient if our programming tools allowed us to do something, say in simulation, that we couldn't implement physically on a device once we get to the device. And vice versa, we don't want our programming tools to restrict us from doing something that we can actually do on a device. And physically, we never can observe the state of the qubit. We don't get this nice vector state representation. We will talk a little later today about how we can extract information from the physical system about the state of the system, but we never get this nice vector representation with the first and second component. And when we manipulate qubits, we also don't send to it instructions, go from this state to that state by multiplying yourself by this matrix. We just don't do it in physics. Instead, we manipulate qubits by applying gates to them. And in our quantum computer, qubits are sort of boxes. We cannot pick what's inside of them. We can just apply operations to them. And this is the representation that Q# uses. So in Q#, qubits are a data type that is similar to a software object in object-oriented programming languages. So it is something that has some internal state, and you don't necessarily have access to that state. In Q# you don't. But rather you can modify that state and get access to some information about that state via special getter operations or setter operations. So this is what Q# gives you. Here you can see an example of Q# program. We will see more of that later today. So when we allocate a qubit, basically the syntax is the same as defining an object variable in other languages. We allocate it, we know that it starts in state 0. Now, we want our tools not just to reflect what's going on physically, but also give us a little help if they can. And this is why when running on a simulator, so running locally on your computer, we take advantage of the fact that simulator actually knows what the internal state of the qubit is, because it simulates it. So there is a very helpful function called dump machine that allows you to peek at the state of the qubit to see where your program is headed. You're not going to be able to get the same capability when you run on hardware. But if you run on simulation, for example, if you are just learning the basics of quantum computing, or if you are running your program on a very, very small instance of a problem and you want to see what went wrong, this is extremely helpful. So what this code snippet does is allocate a qubit and immediately see what its state is using dump machine. And if you do this, you will get the basis states, and you will see that the amplitude of the 0 state is 1 and the amplitude of the 1 state is 0. This is exactly what we promised. The simulator allocates the qubits in state 0. Now, the next thing we want to do with our qubits is to change their states. And again, if we draw some parallels with classical computing. In classical computing, we had bits and we had operations on bits. And the most primitive operations were Boolean logic operators. All more complicated calculations can be represented as combinations of Boolean logic operators. Those were described by truth tables. For example, here is the truth table for a single bit operation, not gate. You see that it converts 0 to 1 and 1 to 0. In quantum computing, our data is more complicated. It is vectors. And the best way to modify the state of a vector is multiply it by a matrix. And this is what quantum computing does. So single qubit gates are matrices. And since single qubit states are vectors of length 2, our matrices that represent single qubit gates are 2 by 2 matrices. And the effect on the qubit state is defined using matrix multiplication. Let's see what kind of operations there exist classically and what kind of operations there exist quantumly. Because this is not going to be a one-to-one correspondence, and that makes a lot of sense. So classical operations on 1 bit, there are only 4 of them. If you just write out all the truth tables you can, there is identity operations that doesn't change the state of the bit. There is negation, which changes the bit to the opposite one. And there are constant 0 and constant 1 operations that just always output 0 and always output 1. Here on the right, you see how we can represent those operations if we want to be fancy and try and represent our classical computing in the same terms as quantum computing does. And we can always do this if we just say that the top element of our vector is 1 if it's 0 and 0 otherwise, and the bottom element of our vector is 1 if the bit value is 1 and 0 otherwise. So we can represent those operations as matrix operations as well. Are all of them going to be available to us in quantum computing? No. The important thing about quantum computing is that all gates must be reversible. So given the gate you want to perform and the result of its application, you have to be able to find the input that was passed in this operation. This is basically just how the physics work. Basically everything in quantum computing is defined by this is how the physics work. This is the simplest mathematical model we could come up with to describe the physics. So in matrix notation, you need to have the inverse of this matrix to figure out what the input was. And this means that the matrix has to be invertible. Now, there are some classical operations which are reversible, the ones which permute the inputs. And there are some that are not reversible. Those are the operations that erase information or that override it. So you can implement identity and negation operations, but you cannot implement constant 0 or constant 1 operation. If you think about it, if you have a constant 0, for example, if you know that the result of the operation is 0, you don't know whether the input was 0 or 1. So it's not reversible, cannot implement in quantum computing. Identity and negation are reversible, so their inverse is just themselves. So we do have their equivalents in quantum computing. The identity operation translates to identity gate. It has this nice diagonal matrix, and what it does to the qubit is basically nothing. It is convenient in a lot of mathematical representations in discussions of more sophisticated algorithms, but on its own, identity gate doesn't do anything interesting. Negation gate, on the other hand, is one of the more useful gates in quantum computing. It basically swaps the top and the bottom elements of the vector. If you see the formula, you start with C0, C1, and then you end up with C1, C0. We also call it bit flip gate. Why? Because if we use the cat notation, the Dirac notation, we see that it converts cat 0 to cat 1 and cat 1 to cat 0. Since we very often describe quantum gates in terms of their effect on basis states, it makes sense to describe it this way. It basically takes the basis state and flips it to the other one. Now, let's see some gates that exist in quantum computing, but do not exist in classical computing. If we didn't have anything like this, and we would be just limited to a subset of classical operations, that wouldn't be very interesting. So the first and probably the most popular of such gates is Hadamard gate. It has this kind of matrix, and you see that it's not a diagonal matrix and it's not an anti-diagonal matrix. It has all 4 elements non-zero, which means that it takes a qubit in a basis state that has a classical equivalent, and it puts this qubit into a state of superposition in which both basis vectors have non-zero coefficients. It actually puts them in equal superposition, states in which 0 and 1 have equal amplitudes, or equal amplitudes differing by 1 sign. So you can see that applying the Hadamard gate to 0 state gives us superposition 0 plus 1, and applying the Hadamard gate to 1 state gives us superposition 0 minus 1. Those 2 states are important in quantum computing. They occur in a lot of algorithms. So they have their own special notation. They're called plus state and minus state. Remember that the symbol in the cat notation is just a variable name. So this state is just a state named plus. Another interesting thing about the Hadamard gate is that it takes a qubit in equal superposition state and puts it back into the basis state. So we can transform both the basis states in superposition states and the other way around. We're going to make use of both these properties today. And the last gate I'm going to introduce to you today is phase flip gate. This gate is probably the least intuitive of the ones I'm talking about today, because it not only doesn't have a classical equivalent, it doesn't have a nice explanation like it is a gate you use to put in superposition state. Rather, it is a state which operates on the phases of the basis states. So it changes the sign of the coefficient that is attached to the state. So you see that it leaves the 0 state unchanged, and it multiplies the coefficient of the 1 state by -1. If you apply it to the basis state, you're not going to observe any difference. We will talk in a moment about measurements, and there is just no way you can observe this change. But this gate makes a lot of sense when you apply it to superposition states, the states in which both 0 and 1 coefficients are not 0. Because in those cases, you can actually notice that something changed in the state. So if you apply the Z gate to the plus state, you get the minus state. And from minus state, you get plus state. We're going to take use of this property later today again. This is a lot of information to take in, especially if you're not super familiar with matrix multiplication. So here is a little trick I use to visualize things a little. If you draw the states on this unit circle that I showed you earlier, you can think of all these 3 gates as reflections around a certain axis. And you're going to only need those states that are shown on the circle for today. So you can just kind of memorize these transformations. So you can see that if you take X gate, it changes 0 into 1 and 1 back into 0. If applied to the plus state, it doesn't do anything because plus state is 0 plus 1, 1 plus 0, same difference. So it has shown that it preserves the plus state. And the minus state, it converts to a state with an extra minus phase. So all the way to the other side of the circle. The Hadamard gate converts one state to minus state and 0 state to plus state, and vice versa. Then, if you look at the Z gate, it does a reflection across this horizontal line. So it doesn't change anything about the 0 state. It converts one state to minus one state, and it converts plus to minus and vice versa. So the reflection axis is horizontal. Also, the states on the opposite side of the circles differ by a coefficient of -1. It's called global phase, and it is a thing that you cannot observe, but in some cases it is important. For today, it's not going to be important, so you can assume that circles on the opposite side, that points on the opposite side of the circle are just the same. Another state machine, yeah, it's just nice to have visual aids rather than do matrix multiplication from scratch every time. Shows you just how those gates affect the basis state 0, 1, plus and minus, how they move them between each other. How do we represent quantum gates in Q#? So since we discussed that we don't get access to the internal state of the qubit, we basically it's not that convenient to represent operations as matrices every time you want to apply a gate. So we take kind of operational approach. We say that gates are just operations which have side effect of changing the internal state of the system. So if you apply a gate to a qubit, it will not give you the output. It will not give you the state of the qubit after the gate, like this equation shows you. So if you want mathematical representation, you write Hadamard gate multiplied by the 0 state equals this new state. In Q#, you just write apply H gate to qubit Q. Some gates will also have parameters, not today. And the internal state of the system, of this qubit Q that we allocated here, will change from 0 to plus. But basically, this is not represented in the code. It is something that we are going to observe based on the dump machine output. And here you see that the dump machine indeed shows us that amplitude of both 0 and 1 states is 1 over square root of 2. Basically, just like this math promises us. So we know how to allocate our qubits and we know how to make transformations on their state. But so far, we didn't do anything that allowed us to get information out of the system. And this is sort of important. You cannot really have an algorithm which just does something and never lets you know what it did. That's not what algorithms are for. So how do we do information readout in classical computing? In classical computing, it's actually very simple. All your values computed during the algorithm are just normal numbers, 0 or 1. So you can just look at that value and read it, and nothing's gonna happen to that value from the act of you looking at it. In quantum computing, I have mentioned once or twice already, the state of the qubit is not directly observable. So you are getting a lot less information out of the system than is actually used to describe it. And the second thing that absolutely has no equivalent in classical computing, is that when you observe the state, it's not a passive action, it's an active action. You change the state by observing it. And the operations that we use to read out information of a quantum system are quantum measurements. So if you measure basis states, this will actually still behave like classical computing. If you measure 0 state, you will get 0. If you get 1 state, you will get 1, and the states are not going to change when you do this. But if you measure a superposition state, there is no equivalent for superposition state in classical computing, and there is no equivalent for measurement of superposition state in classical computing. If you have this state with two non-zero coefficients, C0 and C1, we will get measurement result 0 with probability square of C0 and result 1 with probability square of C1. And most importantly, the qubit state is going to collapse to the corresponding basis vector. So if you measure 0, the state of the qubit is going to become 0. If you measure 1, it's going to become 1. This is important because the coefficients C0 and C1 carry much more information than just one bit you are going to get out of the system when you measure it. And when you measure the system, you destroy its state. So you return to it, try to measure again. You cannot get any more information about C0 and C1. You get just one shot at this measurement, and you get just one bit of information out of it. So this is why quantum computing is sometimes described as trying to drink an ocean through a straw. You have this ocean of computational power, of the expressiveness of how you can represent the quantum states and operations on them. But the way you get information out of it is just a straw. You get one bit from each measurement, which means we need to get clever when we do our algorithms. And measurements in Q# are very similar to the gates, except they actually have a return value. So they are also operations that take qubits as parameters. They change the state of those qubits as a side effect, and they return the value of result data type. So here, for example, if we write a code which allocates the qubit in 0 state, applies Hadamard gate to it, and then measures the qubit, prints the result, and looks at the state of the system afterwards, it's not going to give you a superposition state any longer. It's going to give you the measurement result. In this case, it was measured to 1. And the state of the system is going to change to 1, which you can see here on the graphic. Okay. So we learned what the qubits are, how we describe their states, how we change their states using quantum gates, and how we get information out of the system. And this is actually enough to get our first quantum application running. Let's look at how to implement random number generation in Q#. The interesting thing about random number generation is that there are two ways to generate random numbers. True random numbers are generated using some physical phenomenon, like the tiny fluctuation of temperature, the photons, something like this. Pseudo-random number generators don't actually generate true random numbers. They are mathematical constructs that give you numbers that are actually deterministic sequence. It's just that it's deterministic in a complicated way, in a way that has some properties similar to the true randomness. So for a lot of applications, pseudo-random numbers are perfectly fine, but for some of them, we want real random numbers. And in quantum mechanics and in quantum computing, measurement is such fundamentally random thing, a source of true randomness, because it's not some computation that brings us the measurement result. It's not some hidden variables that define it. It's a proper physical randomness process. So if we prepare a qubit in superposition, in equal superposition, and just measure it, it will give us a random bit, 0 or 1, with 50-50 chance. And it's going to be true randomness. Here is the code that does it. We define a variable that tells us how many bits we want to generate, and we want to count how many of them were ones. So we can do allocate the qubit and repeat as many times as we want the simple process of applying Hadamard gate to it to put it in equal superposition, and then measure it. And here we don't do with those generated numbers, except we count them. So if the measurement result is 1, we increment our counter of ones. And in the end, we tell, here is how many ones were generated out of all your runs. In this case, when I ran this code, I got 52 ones, which sounds random enough. And I actually ran it several times and got different numbers, just in case it would be hard-coded or something. And this is the first hands-on portion we will get today. Now you have several options. If you have the opportunity to download and install the QDK beforehand and download the quantum katas locally, then you can do it locally. This is going to be what I will be doing to show you. If you don't, but you want to follow along and try to solve some tasks yourself, you can pick any of these links at random. They're all aka.ms/try quantum katas 1, 2, 3, or 4. Please pick an instance at random. It will bring you to an online version of the katas, Jupyter notebooks hosted on Binder service. And you will be able to run exercises there. If you just want to follow along but don't really want to do the exercises yourself, you have that option. I will be taking a couple minutes break after I talk to you about the exercise, and after that I will show you how it's solved. Now let's see how to run stuff. If you are running locally, like I am, you navigate to the folder which has quantum katas, and you run Jupyter notebook index IPyNB. These instructions are also in the quantum katas repository, so if you lag behind, you can look them up there. If I do this, it brings me up a browser and Q# Jupyter notebook, which brings me to the main page of the quantum katas, the list of all tutorials that are available. Let me make the letters a little bigger still. Right now we're looking at random number generation tutorial number 7 in the list. So let's run that. This tutorial is in general designed for self-paced learning, so it gives you some background information, which I pretty much gave you already. You need to execute these first 2 cells, and you need to execute them regardless of whether you are running locally or on Binder. They prepare your environment, basically pull up the necessary testing harnesses and make sure that they will be recognized by your code. After this, there is a little introduction, which basically repeats the principles of how you would build a random number generator. And here is the first exercise. Generate a single random bit. So it gives you the descriptions of the input you have, which is known. It gives you the goal, generate 0 or 1 with equal probability, and the operation that you need to implement. So this operation returns an integer, So you know that you will do return 0 or return 1. And this code is actually so nice that it already allocates a qubit for you. And if you need, there is this hint that tells you what to do inside this allocated block. And I would also do exercise 2, which is generating a random 2-bit number, which is going to be very similar to generating 1-bit number, but with 2 numbers. So to execute the cell, you check that your first 2 cells completed execution. You should get something very close to this. And then you take this cell and you run Control-Enter. And it's going to say, well, I didn't do anything to solve this task. So it will give you the error message telling that you returned -1 and you needed to return 0 or 1. If you do something smarter, it's going to give you feedback on what you did. And if you did correct, you will get success. Now, let me take a small pause to give you a chance to look at those exercises. And then we will return and I will show you how to do them. And we will move on to the more interesting part, the real algorithm. Okay, another 30 seconds, and then I will go in and just tell you the answer. Okay, so the first hint just tells you what to do, so you just need to implement it. Use the allocated qubit. We already have a qubit. Apply a quantum gate to it. We have learned 4 quantum gates so far, and 3 of them are not going to get any interesting effect on our qubit in state 0, but the Hadamard gate is going to put it in equal superposition, and that's what we're going to do here. After this, we need to measure it. That's measurement operation. But the return operation of this measurement is not an integer. So if we try to run this code, we will get error message. The type result of the expression is not expected return type int. So what we are going to do is convert it to an integer using a ternary operator. So we check if it is 0, 0 is a built-in constant that corresponds to result measurement 0. So if it is 0, we return 0, otherwise we return 1. This is a ternary expression very similar to what, for example, C++ has. And if we run this, we actually generate a random number with success. Big success, I would say. Now, when we generate a 2-bit number, we can, of course, do the same. We can allocate a qubit, apply Hadamard gate to it, measure, allocate another qubit, apply Hadamard gate, measure. But remember how our programming tools are supposed to help us be more productive. So what we can do, we can take these operations that we defined here previously and just use it. So we know that if we take a random number, a random bit, and multiply it by 2, and then add another random bit, it will just give us a random number in the right range with the right probabilities. So you see that here we already don't use any quantum-specific constructs. All our quantum-specific constructs were left in this first exercise, in which we actually used qubits and gates and measurements. And the second one is just taking advantage of what we did before, without exposing any implementation details to the end user. So this allows you to implement high-level algorithms without always thinking about just the qubits and the measurements. You can think on a higher level if your language allows you to do this. And C# allows you to do this. Okay, I'm not going to go through the rest of the exercises. I encourage you to do this offline. But we are limited on time today. So now let's get back to the second part of our presentation and look at an algorithm that actually allows us to do something that a classical algorithm does not. And this problem is actually the simplest thing that we can use to demonstrate how quantum computing works. It doesn't solve any practical problem other than teaching people. And this problem is actually so important that this algorithm is a part of probably every single quantum computing course that exists. Maybe there is 1 or 2 exceptions, not more. So let's say someone gives you a box that contains a function of 1 bit. And we have already seen all those 4 functions: identity, negation, constant 0, constant 1. And you don't know which function it is. You cannot open the box and look into it. What you can do is you can feed inputs into this box, and it will give you the outputs. So if you feed a 0 in it, it will tell you what the value of function of 0 is. And if you feed 1, it will give you f of 1. So how many queries do you need to identify this function? Classically, just 2 queries. There are 2 different inputs, and if you just query one of those inputs, you are not going to get all information. You're going to narrow down your candidates to just 2 out of 4 functions, but it's not a definitive answer. You will need a second function to basically exhaust all options. It turns out that on a quantum computer, to answer this question, you also need 2 invocations of the function. But here is something interesting. Let's ask a different question. Let's say you do not care which function exactly it is, but you care whether this function in the box is a constant, always returns 0 or always returns 1, or variable. Does it have the dependency on the input? On a classical computer, this is the same question. You still need to identify the function precisely before you can answer that question. And you still need 2 queries. But on a quantum computer, you can do it in just 1 query, in 1 function evaluation. And In just a moment, I will show you how to do it. And this problem demonstrates a very profound thing about quantum computing. This simple change of question changes it from a question about every value of the function, a question that requires evaluating the function on every input, to a question about learning a global property of the function, a property of all values on all inputs at the same time. And it turns out that this is something that quantum computing is good at. If you need to compute your function on every value and get all the results, quantum computing is not going to help you. Even if you compute the function on the superposition of states, remember how measurement only gives you one result out of all multitude. This is going to be what narrows down your ability to take advantage of it. But if you need to learn a global property of the function, you can engineer a clever algorithm that will basically cancel the options that you don't need, the options that are not the answer to a question, and amplify the options that are answers to a question. And then when you do the measurement, you will just get the results that is your answer. This is called interference, canceling out the things you don't want and amplifying the things you do want. But so far it's been a bit hand-wavy. Let's look at how exactly this looks in implementation. And to implement these algorithms, we first need to discuss how we can implement this classical function in a quantum way. Because if you only have the access to the function in a classical manner, you cannot build a quantum algorithm around it. You would still need at some point to ask what the value of the function is, and you will only be able to do this in a classical manner. Instead, you want to implement this function as an operation, a quantum operation that has equivalent effect. There are some problems with this, so it hides away all the implementation complexity. You can define an oracle that just solves the whole problem, and it's not going to be helpful for you. But in this case, we are going to define it in a way that is just the right size. So the phase oracle is the kind of oracle we're going to use this time. And it encodes the value of the function into the phase of the state. Here is the mathematical expression for this. So you see that if you feed a basis state into this oracle, you will get the same basis state out. I'm hearing some echo. Does somebody need to mute? Then you get the same basis state, but with a phase that is -1 raised to the power of the function. It looks rather mathematical, but if we think about it in simpler terms, if we just look at the cases, if the function of x equals 0, then the phase of the state just doesn't change. And if the function is 1, the phase is multiplied by -1. This is all it means. And this definition tells us how to use the oracle on the basis states. The part which a lot of oracle definitions sort of gloss over is you need to also be able to define its behavior on the superposition states. And this means that we need expression for the case when the input is superposition. But this is actually defined implicitly. Your basis state defines the effect on it, and the effect on linear combination of basis state is just a linear combination of effects on individual states. So if you implement the operation in a quantum way, in a way that only uses quasi-quantum operations, so that you never break superposition, and if you verify that it does the correct thing on the individual basis states, then you need to you don't need to worry how it behaves on superposition. It is going to behave on superposition in the correct way automatically. We will not spend a lot of time on the details of implementing the oracles. It's a fascinating topic in general, but we just don't have time for it today. But let's take a very quick look about how to implement the quantum oracles for our one-bit functions. Oh, and I actually hope that nobody is thrown off by the term oracle. I actually got a question once that started like this. I don't believe in fairies, elves, and oracles. I believe in math and physics. Please explain it to me using only math. It's not that kind of oracle. It's just a complexity theory term for a box that does something you want it to do, but we don't care how exactly it does. It's used both in classical and in quantum complexity theory. So back to our implementations. If we have the function that is constant 0, let's write out the behavior of our oracle on both basis states and see what it looks like. And actually, if our function value is 0, then this extra phase, -1 to the power of the value of the function, is always 1. So both 0 and 1 states remain unchanged. And we have seen this gate already. It's the identity gate. This is so simple an implementation, you literally don't need to do anything to implement it. My favorite kind. The second function we will look at is the identity function. If value of the function is equal to its argument. In this case, if we do the math, we will see that the 0 state doesn't acquire any phase, but the 1 state acquires a -1 phase. And if we write this out in matrix form, we will recognize that this is exactly our phase flip gate, the Z gate, because it takes the 0 state and leaves it unchanged, and the 1 state becomes -1 state. So this is slightly more complicated implementation. It needs 1 gate. And you can analyze constant 1 and negation similarly using the state machines that I showed earlier. I will not go deep into this in the interest of time, but basically a reasonable combination of Z gate and X gate will allow you to get those phases in the basis states that you want to use them. Okay, so now let's look at how okay. Minor technical malfunction, slides out of order. Now that I have convinced you that we know how to implement the oracle, and it's the important building block because without it, we don't have this box on which we're doing the analysis. Let's see the algorithm itself. And it's actually a very simple algorithm, just a couple of gates. We start with a qubit in 0 state. That's what we always do in quantum computing. Then we prepare an equal superposition on states on this qubit using a Hadamard gate. This is also a very, very common opening in quantum algorithms. If you're not certain what to do, prepare equal superposition. Then we apply the oracle to this superposition. Remember how before we discussed that if we want to detect changes in phases of the basis states, detect whether they acquired that minus sign or not, we want to apply those gates in superposition. We want to look at superpositions so that we have something to compare those phases to. So in this case, we get both 0 state and 1 state acquire corresponding phases. We would need to do a little case analysis here, but the summary is going to be this. If we have a constant function for which the value of x from 0 and from 1 is the same, in this case, both 0 and 1 states are going to acquire the same phase. We can move it out of the brackets and say that it's either plus this state or minus this state. And this phase, the global phase, the phase by which the whole state is multiplied, is not actually observable. But if our function was variable, so the value of f of 0 is different from f of 1, then the signs of our 0 and 1 states are going to be different. One of them is going to be plus and the other one is going to be minus. Again, we can write it a little concisely like this. And we see that these states are actually different. And to observe this difference, we need to apply the Hadamard gate again. And if we had this state 0 plus 1, it will become 0 state. But if we had 0 minus 1, it will become 1 state. And the measurement allows us to actually distinguish those states, 0 from 1. And in this way, we basically did clever engineering of our system so that it calculates the value of function on both 0 and 1 input. But since we cannot have access to this information directly, we do this trick of applying Hadamard gate to combine those results to give us exactly the outcome we need to get, to give us exactly the bit that tells us whether the function is constant or variable. And you can follow these state transformations on this circle diagram as well. We start with the 0 state. Then we apply Hadamard gate to it to get to our plus state, 0 plus 1. After it, we apply the oracle, and it either leaves this state at plus, it moves it to this minus plus state, or if it is a variable function, it moves us to the minus state or minus minus state. Yeah, it sounds terrible, I know. And then the Hadamard gate moves the plus state back to 0 or the minus state to 1. And those two you can actually distinguish by measuring. Let's see how this algorithm looks implemented, because this slide doesn't look really like implementation, it's all mess. So if we look at how we would implement this, so that on one hand we can have our oracle in a box and not expose its intrinsics to the algorithm, because what we don't want to do is for our algorithm to peek inside the box and to just tell there is nothing there. Of course, it's a constant 0. So quantum oracles are just operations. They are operations similar to quantum gates. They take qubits as inputs. In this case, it's just 1 qubit. And it doesn't have any return. So its only effect is the change of the state of this qubit. Here we define 2 oracles, one for constant 0, and we saw this just identity gate, or we don't need to apply identity gate, we can just leave the qubits alone and do nothing to them. And The second one is identity function, which we have seen corresponds to the Z gate. So we get the oracle, we perform some gates on it, and the result of this operation is the change in the inner state of the qubit. Now, when we think about the algorithm, this is function balanced. It takes this oracle box as the input. It is an operation that is passed as a parameter to the algorithm. In Q#, operations are first-class citizens. It has elements of functional programming. So you can assign them to variables, you can pass them around as arguments. And in this case, we are taking the oracle. And this algorithm basically doesn't have a way to pick inside this oracle. The only thing it can do is apply this oracle to a qubit. And that's exactly what it does. It allocates a qubit and goes through all the steps we just discussed. Applies Hadamard gate to this qubit, applies the oracle to the qubit, and applies Hadamard gate again. And you see that applying the oracle, which is actually a parameter, is the same as applying Hadamard gate. It doesn't differ in syntax at all, except it's highlighted differently because Hadamard gate is built in and oracle is not. And then you measure this qubit, and it's again a similar construct as I showed to you in the random number tutorial. It does the measurement, compares it with the 0 measurement result. If it is 0 measurement result, then the function is not balanced, and we want to return false because the operation is called is function balanced. But if the measurement result is not 0, it's 1, then we know that the function is balanced. And finally, we can put all these pieces together if we call this function with one of these operations as a parameter. And this is basically what it does. So the stuff in those squiggly brackets is call of a function with operation as a parameter. And then we're printing the results. So if we run this algorithm, we get false for the first question, and we know that constant 0 is indeed not a constant function. And we will get true for the second one. So we know that identity is indeed a balanced function. This is it. This is Deutsch algorithm, the absolutely simplest thing you can do to show that quantum computing has the capabilities that classical computing doesn't. This algorithm takes advantage of both superposition and interference, because basically this step, applying Hadamard gate, actually sort of splits each of these terms into two, and then the terms that we don't want cancel each other out, and the terms we want to get amplify each other. So this is something interesting, something that classical computing cannot do. But if we think about it from a different point of view, we got a speed up of taking one query where in the past we used 2 queries. And that's not super impressive, especially if we consider all the math we needed to learn for this and all the steps we needed to take, not impressive. So we can take the same problem and make it a little more impressive. Generalize it to Deutsch-Jozsa algorithm. If we have functions that act on n bits rather than on just 1 bit, and they still return 0 or 1. And our promise for this function is slightly different this time. We are not considering all possible functions. Rather, we consider constant functions, the functions that are 0 or 1 all the time. Or it is a balanced function, function that returns 0 for half of the inputs and 1 for the other half of the inputs. This is a smaller class than all possible functions, but still it's a pretty broad class. And you want again to not figure out which function exactly it is, but rather to figure out whether it is constant or balanced. Now, what happens in a classical world? You send a query to the function. You get a reply. Let's say it was 0. You send another query with a different input. If it was 1, you know that you got 2 different inputs, 2 different outputs. And this means it's not constant, so it's balanced. But if you got 0 again, you need to keep querying the function, because it's possible that it's still balanced, but you just got unlucky. In the worst case scenario, you will need to go through half of the inputs that will all return 0, and only the next one will return you 1 to tell you that, yeah, okay, it's still balanced. So this is worst case scenario complexity is exponential. In quantum world, you can still do this with just 1 query. I'm not going to go into the details here because we didn't actually cover multi-qubit systems, the math behind the multi-qubit gates, but the algorithm itself is very simple. And once you learn how multi-qubit systems work, it's very similar to the Dodge algorithm. So you start with qubits all initialized to 0 state, apply Hadamard gate to each qubit. This prepares an equal superposition of all inputs. Then you apply the oracle, which is defined very similarly. It flips the phases of inputs that are solutions to f of x equal 1. And then you apply Hadamard gate again. This again gives us interference. And now if you measure all qubits, if all measurement results are 0, the function is constant. Otherwise, it's balanced. So it's an exact generalization of what we saw before, but for multiple qubits. And this is what we're going to explore in our hands-on exercise number 2. Because it wouldn't be fun to implement Deutsch algorithm, which I already showed to you, right? We need to stretch ourselves a little. Now, again, we are using the same repository, the same links. If you were running the quantum katas locally, your session is still good. If you were using one of those links, it probably expired for an activity, so you need to create another one. And again, please use a random link of these 4. Okay, I was running it locally, so my session is still good. We get to the same index notebook, and we are looking now at the next tutorial, exploring Deutsch-Jozsa algorithm. This is again a self-paced tutorial, and it's a pretty long one, much longer than random number generator. Let's start executing these 2 cells, and then I will walk you through the content of this tutorial. We are not going to be doing all of it right now. You're most welcome to. It's a fun tutorial. I like it. But it covers a lot of stuff that we already discussed, but it gives you all the math necessary. It gives you the problem that we are solving. It gives you examples of constant and balanced functions. It walks you through implementing classical functions in Q#. Q# has certain elements of classical programming language, since it needs to be able to express fairly sophisticated classical computations that are necessary to perform quantum computations. So you can implement these classical functions in Q# classically. It looks very similar to any other language. Then it gives you an exercise on implementing a classical function in C#, which I'm going to skip. Then we discuss the classical algorithms. And the next exercise is implementing the classical algorithm, basically the thing I just described for you. And again, we're skipping it for now. Then it defines quantum oracles. It walks you through the example of Deutsch algorithm again. It talks to you about how to implement oracles in C#. It is very, very similar to what I showed you right now, but generalized to multiple qubits. Then there is an exercise on implementing a quantum oracle in C#, which I'm also going to skip. But we're getting close to the thing I'm not going to skip. So the quantum algorithm itself, it walks you through all the math of what's happening when we flip the phases of half of the basis states. And finally, after all this scrolling, you get a summary of the algorithm, which is exactly the same we've seen before. And we get the exercise we're going to do now, implementing the quantum algorithm. You see that the signature of this algorithm is slightly different than what we've seen before. It gives you two parameters. The oracle, that is this box, which this time is going to be applicable to an array of qubits, and the number of qubits that you need to apply it to. Then you get the outline of the algorithm, and since it's a self-paced tutorial, it tries to really help you figure out what each step should do. So it points basically what you need to do. Every place that is marked with ... means you need to write something there. You need to figure out what is the initial value of this variable. You need to figure out how many qubits you need to allocate. Yeah, I know it's very subtle. It tells you it right up front. Then you need to perform each step of the algorithm, apply Hadamard gate, apply the oracle, apply Hadamard gate to each qubit again, and then the measurements. And then you return the value. This exercise points you to the documentation on C# control flow. You're going to be using it for doing something to each qubit. And I think other than that, you are equipped to be dangerous at this point. And again, this tutorial gives you the feedback again. So if you execute this cell, it's going to complain to you that there is syntax error in expression, which makes perfect sense because ... is not a valid part of C# language. But once you replace these ... with meaningful expressions, you will get the feedback on whether your solution is correct or not. Let me give you 7 minutes until 57. And then I will take the last 3 minutes to walk you through the solution before I hand off this session to Ryan, who will show you how to run the same algorithm on Azure Quantum. Time starts now.
And Maria, please feel free to mute if you wish.
Did I do something embarrassing?
No, just preventing that possibility. Hey folks, we just have a few more minutes left for this exercise time, and then we'll get back to the explanation. Thanks.
Okay, so let's look at how we're going to solve this task. So first of all, our default scenario is going to be assuming that the function is constant. So we're going to say if the initial value is going to be true. Now allocate an array of n qubits. Easy. Just the parameter we're given n. Now the first step is to apply Hadamard gate to each of the qubits. If we want to do it kind of in an old-fashioned way, we can iterate over all qubits in the array. This is sort of a for each loop equivalent in K-sharp, and apply Hadamard to each individual qubit. Then we apply the oracle to the input register. Same syntax as applying an operation. Same syntax as we have seen in the past, except now the parameter is an array of qubits rather than a qubit. Now apply a Hadamard gate to each qubit again. Let me show you a different way to do it. The Coleman suggested to use apply to each library operation. It takes two parameters. The first one is the name of the gate, and the second one is the register for which you need to apply this operation to each element of. So that's another way to do the same thing. And now the most interesting thing. Measure each qubit of the input register. So we want to do the same thing we did before, iterate over all qubits. Measure each qubit. We have seen that before. Measure the qubit. But now we're doing something different. We are not returning this value immediately. We are updating the variable. So what we are going to do is if the measurement result equals 1. Remember, our condition is we need to check that all the measurement results are 0. If they're all 0, we've got ourselves a constant function. If at least one of them is 1, it's balanced. By default, our variable is in true state, so it's constant. So if we ever get a 1 measurement result, we need to set it to false. And that can be done like this. Now we don't need to do anything else other than just return the value of the variable. And let's see whether I got it right. I did. So I hope you were able to figure out this task yourself. If not, I highly recommend you to return to this tutorial afterwards. All the tutorials in the katas are really good to get started, to get the basics you need to start working with quantum computing, and this tutorial in particular to properly understand the Deutsch-Jaws algorithm and to experiment with it. And at this, I will hand off to Ryan, who will walk you through the running of quantum programs on Azure Quantum. I'm not saying goodbye to you. You will hear back from me again at the end of the day when I will talk to you about our amazing community. Ryan, you get the screen?
Yes, thank you, Maria. Thanks for that awesome introduction. Hopefully all of you are feeling very excited about writing quantum algorithms now. And so I'm going to show you how to do this on Azure Quantum. So just to introduce myself, my name's Ryan Schaefer. I'm another software engineer on the Microsoft Quantum team. I work on the developer experience for both the Quantum Development Kit and Azure Quantum. And I'm a software engineer by background, and so I've been spending the last few years getting familiar with quantum computing. But I'm really excited about the opportunity that Azure Quantum provides, really, to make quantum computers available and accessible to everyone, regardless of your credentials, your background in quantum computing. Right? I think that's the message that that we've been trying to deliver to you in all the sessions today. So I'm really excited to give you a kind of a step-by-step walkthrough of executing these quantum algorithms through Jupyter Notebook on Azure Quantum. So let me share my screen and we'll get started. So what you can see here is an Azure Quantum workspace that I've created. And this is essentially what you saw if you were in Mike's session earlier. It's just the workspace inside Azure Portal that I've already created. And you can see that I've already added some providers to this workspace from our partners, INQ and Honeywell, who are both partners who are providing hardware targets for quantum execution through Azure Quantum. So this is all I need. Once I have my Azure Quantum workspace with these providers, I'm ready to go, and I'm ready to start executing my code. So let's go ahead and do that. I'm going to do this again in Jupyter Notebook. Some of you may have installed this already. Unfortunately, if you don't have access to Azure Quantum yet, since it's still in a limited preview, you may not be able to follow along with me step by step. But these will be recorded sessions, so you can always refer back to this later. But the installation is relatively straightforward. There's only a couple of commands if you've gone through this, and it's relatively easy to get started. So in order to get started, I'll just go to a command prompt where I've already installed the Q# and Jupyter Notebook packages, and I'll just type Jupyter Notebook to start this. And this will go ahead and open up the Jupyter Notebook, the file browser. And when you have this Q# Jupyter kernel installed, it's very easy to just go ahead and create a new Q# notebook by just clicking New and then Q#. This would create a new blank notebook for me to go write the code that I wanted to write. I've already created a walkthrough notebook for this session, so I'm going to go ahead and just open that one. And again, this is a Q# Jupyter Notebook. This is the same environment that Maria was just showing you where the catas were running. And just keep in mind, this is one of several ways to submit jobs to Azure Quantum. You may have seen Megan's demo earlier using Visual Studio Code and the command line interface to submit jobs. And everything I'm showing you here can also be done through Python. I'm just staying in this Q# notebook environment for consistency with what you've been seeing throughout this virtual lab. So you can see this is just a Jupyter Notebook. What I'm going to do is switch this into a slideshow mode just for easier presentation. Where it'll kind of show cells individually, but just keep in mind that everything I'm showing you here is just within a Jupyter Notebook. So yeah, let's get started. Let's go ahead and execute some code on Azure Quantum. So in a Q# notebook, as you've already seen, we can define any Q# code that we want by just writing the Q# code directly into a notebook cell. And for example, I'm going to use the same Deutsch-Jose algorithm that Maria just walked us through in detail. And I've got a much smaller version here without comments so that it fits on one screen. But essentially what we have here, I'll just go through the code really quickly. This is the operation that we're gonna go execute on Azure Quantum, and I've called it run Deutsch-Jose algorithm. It looks slightly different than what Maria just showed. The reason being that because I want to run this on a quantum computer, what I want the return value of this operation to be is actually results. This is direct measurement results that will come back from the hardware. And this algorithm is going to take two parameters. One is n, which I'm using to just be the number of qubits that I'm going to use for the algorithm. And then this oracle name, which will just choose for me which of the phase oracles I want to apply. So I have here implemented very simply this no-op oracle, which does nothing. It applies no phase. And then I have this most significant bit oracle, which is just applying this Z gate to the first qubit in the register. And that will implement a balanced function, whereas this was a constant oracle. And so this algorithm should be able to distinguish between those. So as you just saw, I'm applying a Hadamard gate to each qubit. I'm implementing the appropriate oracle. I'm then again applying a Hadamard gate to every qubit. And then there's just another syntax if you want to measure many qubits at once. I'm just returning the measurement of all the qubits. And that'll be the return value of the operation. So all I have to do is execute this cell. And this will go ahead and compile that Q#'s code and make it available for me to work with in the remainder of this notebook. You can see here it's output the operations that it was able to compile. So to work with your Q# code in a Jupyter notebook, you want to use what's called magic commands. So in Jupyter, you have these commands which start with a % that are known as magic commands. And these are sort of the ways you can interact with code without writing the code directly. So I've already written the code that I want to execute. And in Jupyter Notebook, all the documentation, everything you need, you can access directly from, within Jupyter Notebook. You can just run this list magic commands to kind of list, this is all the things that you can do from within a Q# notebook. And then you can pick any one of these and kind of get more detailed usage information by just appending a question mark here, and you'll get some more details on how to use that command. And so that's what we're going to use in order to interact with this Q# code that I've written. The first thing I'll show you, which Maria already showed you earlier, is this simulate command. So I have my Q# operations, and by just using this simulate magic command, I can execute that operation by passing whatever parameters I need. So all I have to do is type simulate %simulate, and then I'm going to copy paste this so I don't make a typo. But basically the name of the operation followed by the argument. So this is going to execute the run Deutsch-Joes algorithm on 4 qubits and use this no-op oracle, which should do nothing. So if I execute this, this will actually simulate this operation locally using the full state simulator and return the results. And you can see I got all zeros, which is what I expect because this was a constant function implemented by my oracle. Again, if I just want to change the parameters here and run it again, I can do that. If I want to use the other oracle, I just change this oracle name to be the most significant bit oracle instead of this no-op oracle. This implements a ballast function, and so I expect the result to be non-zero, and you can see it's non-zero. So you have this cycle where you're, as you expect, you're writing your code locally, you're testing your code locally, you're simulating it. Great, so now I've verified that the operation works. And so what I want to do now is actually execute this thing on Azure Quantum. That's that's what Azure Quantum is there for. We want to be able to take our quantum programs and run them, through Azure on real hardware. So in order to do this, what I need to do is go get the resource ID of my Azure Quantum workspace so that I can connect to it from within my Jupyter notebook. So I'm just going to pop back to here, copy that resource ID from my workspace page. And then I just use this, again, another magic command to connect. And I'll just paste in that resource ID and execute that cell. And this will go ahead and connect to my workspace and tell me which execution targets I have available. This would have prompted me to log in, but I have already logged in and have my credentials cached, so I didn't have to do that. Log into the account that where I created my Azure Quantum workspace. So you can see there are a few targets available here from our partners, IonQ and Honeywell, and you get kind of their current status, so you get an idea of what's going on with the providers in your workspace. So now that I've connected, what I want to do is actually specify which target I want to use. And Megan showed you this earlier with the Visual Studio, in Visual Studio Code, how to do this in a project file. From Jupyter Notebook, you're doing a similar thing. You just want to specify the name of the target that you want to use. Again, for demo purposes, because I want this job to return quickly, I'm going to target this IonQ simulator target. If I wanted to target the hardware target from IonQ, I could just type in QPU, which is the name of their hardware target, and that would work. I'm going to use the simulator for now. And this will go ahead and set the active target in my Jupyter session to be the IonQ simulator target. And that's it. Now I'm ready to submit a job. And so to submit a job, I'm just going to use this Azure Submit Magic command, which is very similar to the simulate that I did earlier, right? I use simulate to run the thing locally. And in order to submit to my Azure Quantum workspace, I'm going to do the same thing. I'm just going to be, submitting the job to Azure instead of running it locally. And so again, I will just put the name of my operation, the arguments that I want to pass to that operation, and then optionally, the thing that I can do with my Azure Quantum workspace is give the job a name, right? Because all of the jobs I submit are going to, be saved in my workspace. I want to give it some kind of a friendly name, so that when I go back later, I know, which job was which. I can identify it. So if I go ahead and submit this job, it will do that. It will compile that operation and submit it to my Azure Quantum workspace. And you can see here the details of the job that was submitted. Now, you notice here it says job successfully submitted for 500 shots. So when I ran the thing locally, it executed only once and it gave me a result. Here it's going to execute on the quantum hardware, or in this case, a simulator, but 500 times. Now, that may seem strange, but there's a couple of reasons for that, right? We know that these quantum measurements in general are probabilistic, right? You may have different results each time you run the algorithm and measure, and so you want to get many results back in order to kind of get an idea of the distribution of the results. Also, quantum hardware is not perfect, and so in order to get good statistics in your results, you want to actually have many runs so that you can, if there are any kind of errors or imperfections, that you can sort of average those out and get a good idea of what the results would be. Just like with simulate, I can submit another job with a different argument. I can use the other oracle, right? So I'm going to do that here just to demonstrate that, but I'm going to use my other oracle here, the balanced function. And so if I go ahead and submit that job, again, I can submit many jobs. I don't have to wait for them to complete. And they'll all be queued up in my Azure Quantum workspace and be ready to, and I'll be able to monitor the status of those. So how can we do that? Well, we can also do that from, we could go back to the Azure Quantum workspace and monitor the status there. It's all there, but we can do it from right within the Jupyter Notebook. Again, I can just run this Azure status command, and this will just show me the last job I submitted. What is the status of it? You can see that it was this most significant bit job, and this job is already completed. The simulator runs very quickly. You can see it only took a few seconds. And once the job has completed, I can also view the results right here from within Jupyter Notebook. I can just run azure.output. And I can see that in this case, because it's a simulator, my results were kind of perfect. I got this 1000 result, which if you remember was the same result we got from the simulator using this oracle. And I got that 100% of the time. And so I got the correct result, what I expect because of the way this algorithm should work. So, so that's great for one job, but I've submitted a bunch of jobs, and I want to be able to view all of those results too, and I can also do that from within the Jupyter Notebook. This is one of the great things about having all of these jobs in an Azure Quantum workspace is everything is stored there and saved. For you to go back to, you don't have to worry about, often you run things in Jupyter Notebooks, you're worried about like, oh, I overwrote that, I just re-executed the cell and lost my result. Well, using Azure Quantum, you have the reliability of Azure and all of your results will be there. So if I just run Azure jobs, this would show me all the jobs in my workspace. That may be too many. I can filter it down to just based on the names I was giving the jobs. I just want to see the jobs where I ran this Deutsch-Jose algorithm. So if I go ahead and execute that, it's going to show me a bunch of jobs, including the ones I just submitted and some that I submitted yesterday. It's going to show me the status of all of these jobs. You can see I submitted some to hardware which haven't made it through the queue yet, and they're still waiting to be executed. There's other ones from the simulator that have results. And so you can have a good idea of kind of all of the things that you've submitted, no matter kind of how complex or how many jobs that you're submitting. You have control over that, and you can see the results. And I can look at the output of any of these jobs again through Jupyter Notebook or from from the portal or from all of the options that we give you to access an Azure Quantum workspace. So if I go back to this job, which was using this no-op oracle. I can just copy that job ID. I can just say Azure output and paste in that job ID. And we expected this, right, to be all zeros because this was the constant function oracle. And so I can see that if I go retrieve the output from that job, indeed, I got all zeros with 100% probability here again, because it was using the simulator and there are no errors there. So this is really the end of the walkthrough. Hopefully this has given you an idea for kind of how simple it is, but also how powerful it is to be able to use Q# and the Quantum Development Kit really to write your code locally, test your code locally, verify that things are working, and then submit your jobs to Azure Quantum, monitor your jobs in Azure Quantum, and really make sure that you can really do all of this seamlessly and take advantage of the cutting edge hardware that is provided by our partners, such as IonQ and Honeywell, as I've demonstrated here in this workspace. So, so with that, I'll go back to the slides, and I just want to point out again, in case you haven't done this yet, please, if you want to try out the Quantum Development Kit, there's short links here. The first link here will take you to the installation page for all of the various ways you can use the Quantum Development Kit through Visual Studio Code, through Jupyter Notebook, through Python. You can interoperate, with Q# from Python and from other .NET languages. And then the second link to the Quantum Caddis, which you've just gotten familiar with from Maria's part. It's a great thing to do, especially if you want to learn more and you want to really spend time and dig in. There's many Caddis there on many different topics, and you can really get a good kind of feel for all the different things that you can do with Q# and quantum programming. And so with that, I'd like to go ahead and close out this portion of the session and hand it back to Matt.
Thank you so much, Ryan and Maria. That was a fantastic session. Judging by the depth of the Q&A and the extent of the Q&A, I think a lot of our attendees found that super engaging and helpful. So thank you for that. Ryan, if you don't mind clicking ahead one slide, please. So just to give a sense on where we're at, we actually are a few minutes ahead of schedule, but I think what I'd like to do is go ahead and just extend our short break a bit. I'm sure people could use a little bit longer break to catch up on some work activities or get a refreshment of sorts. So the time I think will be well spent that way. During the break though, the Microsoft team will stay active on the chat and make sure that we're answering as many of those questions as possible. And that would have us be reconvening at 2:45 Pacific time. So roughly about 24 minutes from now. Yeah, so instead of a 15-minute break, we'll just extend that out to a 24-minute break. So with that, I will go ahead and sign off just now for a few minutes, and we'll stay active in chat while people take a quick break, and we'll see you shortly. Thank you. Hi, everyone. In case you're wondering why we're silent, we're in the middle of our break, and we will be reconvening at 2:45 Pacific time, so in about 12 minutes. Thanks. Okay, hello everyone. Hope you enjoyed this short break. We're ready to go ahead and get started again. Kitty, are you there? Okay, great.
Yeah, can you see me?
Sure.
Can you hear me?
Yep, you're looking. Yep, see and hear you very well. So let me turn it over now to Kitty to take us through some of the great assets we have for learning quantum and to help you perhaps start a new or expand your existing career path. Thanks, Kitty.
Thank you. Sharing my screen. Hello, everyone. Welcome to the Learning Quantum session. It felt like the longest 25 minutes I've waited. I am Kitty Young. I'm a senior program manager at Microsoft Quantum Systems. I'm leading our quantum computing education program. In this session, I will share the resources you can find and use to build a path towards quantum computing. A bit about myself. I did my BA and master's degrees in University of Cambridge and a PhD in Harvard University focusing on experimental condensed matter physics. Before joining Microsoft, I was working in the semiconductor industry. The field of quantum computing is still relatively new. I started learning about quantum computing on my own about 2 years ago. Then I started teaching my colleagues and learned a lot from my peer learners and also worked with a lot of fellow learners coming from different kinds of backgrounds. Two things I realized through my own study. Number one, having a PhD in physics doesn't really mean that one really understands quantum computing or even know about it, even though physics is very helpful. Then number two is that one doesn't need a PhD in physics in order to do quantum computing. I often get questions from people interested in learning asking how they can get started with quantum computing, what do they need to learn, where to find materials. And people may think that they need to know a lot about physics and a lot about maths before they can even do any quantum programming. Actually, you don't. There are basically three key concepts you need to understand, namely superposition, interference, and entanglement. Once you get an understanding of those concepts, then you can need a little bit of maths. Is linear algebra is not going to get very, very deep in terms of maths because it's just linear, so it's not super hard. Then we need some high-level programming language, which we have is our Q# quantum-focused programming language that can help you quickly get started with building algorithms using the quantum language and build quantum application that would help you run on hardware. You can see that Q# here is like a cable car that helps you connect through all these concepts and builds conceptual knowledge into implementations. So where do you find the materials to learn? We have everything that you need to lead you towards your goals. If you want to learn more about general concepts, like these basically three key concepts here, we have hands-on tutorials on MS Learn. We currently have modules on learning how to use the QDK and write your first Q# program. Over here, you will see these two modules. The first one is to use the Q# program and use the QDK to write a random number generator, which Maria also showed in the katas. We also have a module on learning quantum-inspired optimization. You can also find a lot of the conceptual articles on the Microsoft documentation page. Here you have the links of all kinds of concepts that you can read at your own pace, things about quantum computers, simulators, about the language and the QDK, some linear algebra, and also the more concepts that you can read about. There's no physics prerequisites needed for any of these. Also, our documentation provides the learning materials on math that's needed for programming. It includes the user guide and libraries for Q#. For example, over here, you can find the Q# user guide. Just like any computing language, we have a nice menu there. A lot of the questions that people have posted in previous sessions are also covered in a lot of these documentation pages. So as you have seen in the virtual lab, there are examples of algorithms that you can accomplish very straightforwardly using Q#. We have code samples where you can find also in the quantum documentation page. So this has a link from the documentation, which I will show you. In the quick starts, in the tutorials, you'll find all these samples. These are the step-by-step guides that help you build up these different algorithms. You can also find the code samples where you can download and clone as a repository and download the codes and run it on the IDE that you choose. Also linked from here, you will find the katas, but you have also seen these short link to the katas where you can find these exercises where you can try yourself. You have seen already in Maria's demo some examples of the katas. The quantum katas is a collection of self-paced programming exercises and tutorials that help you learn quantum computing. They're implemented using the quantum development kit and is programming language Q#. The name katas is inspired from from martial arts. It's a system of individually trained exercises for practitioners. We have now 20 katas in these folders and also 8 tutorials, which Maria showed earlier too. From very basics to things like basic gates, superposition, to more advanced topics like groovers and Deutsch algorithms, you can all find them. Let's take a look at the superposition as an example. I actually have already loaded up here in Jupyter Notebook. As you have already tried and seen that the katas is a sequence of exercises on one topic. Every kata, every folder, you will find one topic. And from very simple to very challenging, each task gives the learner a description of the problem that they need to solve and asks for them to write code implementing the solution. So most importantly, we have the building checkup is a testing harness to tell the learner whether their solution is correct, which you have also tried earlier. Here you can see a visualization of the qubit states for the output. So the katas implement all of the principles of good learning, learning by doing, immediate feedback, and increasing complexity. They also have answers to the task in the code. Of course, we would recommend you to try these out before you look at the answers. So for some of these katas, like superposition, we even have a workbook that guides you through the thinking and the math that you need to build up the tasks. Also, if you ever get stuck, you can find answers in the reference implementation.Q#, but we would highly recommend that you try this before looking at the answers. By the way, the katas are all open source and free to use. You can also submit issues and pull requests. They are available, as you see, on Jupyter Notebook. And this is what I'm using right now is a download free experience. But if you have other IDEs set up, like Visual Studio Code or Visual Studio with the QDK extension, you can also just clone the katas as a GitHub repository and then run it on the IDE that you prefer. In addition to all these materials, you can find the further reading also directed from the documentation page. And our Q# developers have also written a blog page that help you get more understanding and knowledge about the history, about the language, and how these quantum programs are developed. Just to quickly show you, on the documentation, the very bottom, you can find a list of reading materials if you want to go further outside of the QDK, and the Q# blog is all written by our developers. You can find a very nice set of articles. As you have seen earlier, Azure Quantum lets you run your quantum program on quantum hardware through the cloud on your own computer, wherever you are. As Julie mentioned earlier, right now it's the perfect time for learning. You'll be able to grasp the fundamentals and practice to implement the applications to run on quantum hardware. Just in case you didn't get the links in the landscape cartoon, all of the materials are also linked from the Microsoft Quantum Development Kit website. If you ever visited our website, you'll be able to find this development kit page and get links to the MS Learn and the documentation and read more about the structure of Azure Quantum, try quantum execution and optimization. We also include this survey here as an opportunity for you to directly tell us what are the topics that you are more interested in learning more about. Don't forget that all of the materials that I showed are all open source. All of the documentations, katas, APIs, libraries, samples, they're all held on GitHub. And in the documentation, you can also find how to contribute. In the contributing to QDK, you'll be able to find a list of the GitHub repositories that will host all of these content, and you'll be able to submit issues and pull requests. This is our documentation page. And on the katas, you also find quite a good list of good first issues. So you can already start to contribute and write something with the community. In addition, we have developed a quantum computing course for universities. They are structured assignments and projects. We've been collaborating with many universities, with University of Washington being the first pilot. And students are able to contribute to the QDK and or get even internships. So if you are interested to use the existing course in your own teaching, feel free to let us know. Here is the quantumcurriculum@microsoft.com email address. Lastly, if you would like to learn quantum computing in an entertaining way, or need more intuition with the concepts that I showed earlier, superposition, interference, entanglement, and how they are used in algorithms. I've been teaching every Sunday at Microsoft Reactor and Hackaday U, using comics to explain quantum computing concepts and doing hands-on coding with learners live. For example, here is the Deutsch-Hose algorithm, which Maria showed you. You also tried using Q# earlier. Here I'm using this graphical representation to help people get more intuition into that. Every week I post a new comic page. The class is on Sunday at 11:30 a.m. Pacific time. We use Microsoft Teams to join the meeting. And the past recordings and comics, you can also find a good list of them through the Quantum Computing Through Comics project on hackaday.io. There you go. This is your journey towards quantum, and your journey starts now. Thank you so much.
Hey, Kitty, that was fantastic. Thanks for that. We actually have a couple minutes left at the end, and I saw an interesting question come into the chat that, if you don't mind,
Sure.
I'll put up to you live.
Yeah.
So Time Tree wanted to know a little bit more about how understanding semiconductors from a physics standpoint have helped understanding the physical layer of quantum hardware.
Sure. Yeah. So a lot of the concepts that I showed earlier that do not require quantum or physics background, and it's only when you start to want to do the hardware, it does require condensed matter physics, and it does help if you already had a semiconductor background. So namely that you need to understand, because our quantum qubits are built on physical materials, you need to understand the material properties and the architecture of the chips that you're making, and also including the dilution refrigerator. That's one of the options if you want to cool down your qubits. That whole set of stack hardware, electrical engineering will be helpful, solid state physics will be helpful. But if you just want to do programming, we already made all these materials available, open source, and people can already get practice on those.
That's great. Thank you. I see a couple other questions that would love some of the direct links to some of the resources you pointed to. So just take a minute, maybe when we're done here, and you can pop those in. That'd be great. We'll get the links out. And all this material will be available on demand as well, probably by Monday next week, so people can digest that again and get caught up. Well, that's fantastic. Thanks, Kitty. I appreciate it.
Yeah, I'll post the links in now.
Okay, great. So it's 3:03 right now. I think we're probably, if I talk really slow, we should be able to time our start for the next and final session. But I think it won't be any big deal if we get started a minute early as well, assuming Maria is ready and available. Maria, I see you're active there on the screen.
Ready when you are.
Okay, great. So I think, Maria, you and I have been to a lot of in-person events. I think at this point in the day, when we're winding things down, we're probably at the stage of throwing stickers and T-shirts at people to keep them energized and active. But we can't do that virtually. But what we can do is end the day on what we feel is a really high note, and that's making some sense of what it means to actually build a quantum community. And we're excited to have Maria take us through some of that and hopefully make it personal along the way. So thanks, Maria. Take it over.
Hello again, everybody. Just one more session to sit through and we're done, but it will be a good one. So to close today, I will talk to you about building a quantum community. And actually, the summary is less interesting than the actual talk, so let me skip that. The natural question is, why build a community? So everything you've heard before was so technical and in depth, and suddenly we're switching to something so non-technical. But it's actually an extremely important part of the work of building a quantum computer, because it's not just our goal to enable the technology to build the devices and to construct the software stack that powers that. It is our actual goal is making an impact, empowering everybody in the world to solve their problems. And this is Microsoft's overall mission. And in our case, it's empowering people to use quantum computing technology. And this includes the community, because you can have the best tools in the world, you can have amazing hardware technology, but if nobody uses it, you're not going to have impact with it. So we need to build a community, to use our tools to drive innovation and to make actual impact. And this covers a variety of backgrounds of our community member, of people whom we want to empower. From people who are just starting with quantum computing, just learning the basics and figuring out whether this journey is for them or not, to educators, the people who support this first group in their journey into the quantum world, to software developers and engineers of classical non-quantum backgrounds who have hard problems and need to figure out how to solve them using quantum computing. And of course, to people traditionally considered quantum computing researchers, people who come up with new algorithms and new types of problems that can be solved using quantum computing. And this reaching out to all those people requires different kinds of engagements. From holding events and workshops targeted at engaging the community, showing them that quantum computing is actually accessible to them even right now, and educating them about it, very much like the event which we are holding right now, to helping people teach others quantum computing, like we do with the resources that Kitty showed in the previous session, to just having some fun events, just because learning and having impact is great, but sometimes you just want to have fun, to actually empowering others to take our work and bring it forward for other people. The pictures you see here are from all kinds of events we held back when in-person events were actually a thing. And let me introduce you to a couple of folks from our community, so that it's not just learners and educators and experts to you, but so that you can put the faces to these terms, at least some of them. Our first community champion is Sarah. And basically, if you can think of something related to quantum computing, she probably has done it. Writing a book, developing a library, blog, supporting the community, organizing events. She literally has done it all, or is doing it right now. I'm not even sure how long I need to stay on the slides to allow you to read all of this. Next, Vincent, on the other hand, discovered quantum computing not that long ago, so now he is going through the learning the basics stage, and at the same time he pivoted to help develop the quantum katas repository so that other people can immediately benefit from his learnings. He's actually number 2 contributor to the quantum katas right now after myself. Sarah, a different Sarah, is a success story of somebody who went from not knowing a lot about quantum computing but kind of being vaguely interested in it to actually working in it for a living in a year. It takes, in her case, attending a university course that our team hosted on quantum computing last year, contributing to our repositories, getting an internship with us, and then graduating and joining our team. Now she's working on the C# compiler. Philippe is another example of a classical software developer who is discovering quantum computing and what it can do for people just now. But frankly, how many people can I call out in person in this manner in a 20-minute session? Because we have a lot of people contributing to our repos, helping us with our work, helping us spread the word. And there are people of all kinds of educational backgrounds and professional backgrounds. So here, for example, is a selection of contributors to the quantum katas. Admittedly, I was biased. I picked people who do have photos in their GitHub profiles. It just makes for a nicer slide. But you see that these people come from all kinds of backgrounds, from university students and high school students even, to software engineers for whom quantum computing is far away from their day job, to even people for whom not just quantum computing, but even software engineering is not in their career path, like program managers. And all these people can learn quantum computing with our tools and can actually contribute to it in a meaningful way. This quote here from a high school student who contributed to the quantum katas is something that I consider a testament to our work. People don't think that they are able to contribute to quantum computing, to the progress of this incredibly novel technology, until they have a PhD in it. But this is not actually true. You can contribute even if you are in high school. Even if you are just learning, you can already be part of our community and help others. Now, we looked at some folks from our community, but now let me tell you about a couple things that we do for engaging people in our community. And well, you know, sometimes I need an excuse to throw t-shirts at people. One of these things that we hold yearly so far are C# coding contests. For those of you who are not familiar with the world of online competitions, there is a certain, well, not tradition. Basically, there is a certain culture of classical programming competitions. Good examples are ACM, ICPC, yearly competitions for students, Google Code Jam, Facebook Hacker Cup, Microsoft Imagine Cup, that kind of things. And we figured out why not hold a quantum programming contest. So we did, and then we did again and again. And this year we got over 650 participants from all over the world who solved something in our contest. And I love how it is really worldwide thing. If you see the slide, this is a snapshot of the leaderboard, and we have people from all over the world here. It's Russia, US, Finland, Croatia, I think, Brazil, China, Canada, Japan, Ukraine, India. You get the picture. What kind of problems we give in the contest? They vary quite a lot, from the very simple, very basic problems like preparing a superposition state or figuring out which gate you are given, to tasks in kind of intermediate topics that are also fundamental but also more complicated than the basics. For example, reversible computing. It's a branch of quantum computing that works on implementing classical computations in a quantum way. So, for example, if you need to compute a function, classical, but you need to implement it on a quantum computer because it's part of your algorithm, that's reversible computing. And this year we covered even fairly advanced topics such as quantum machine learning. And these turn out to be a great way to engage community, both to reach new people with the ideas that quantum computing is accessible to learn and to interest them, to give them this career as an option. Because, for example, when I was in university, it just never occurred to me that quantum computing is something I can work on. It just wasn't an option. But now we reach people and we tell them, you know, it exists, it's possible. If you like math, if you like having impact, it is an option. And basically successfully participating in such a competition, it's not a huge time commitment, but it shows people that it's possible for them. It gives them confidence to try things further. And well, we get something out of it too, because people who use our tools in new ways, sometimes in ways we didn't expect, they discover issues, they report them, they send pull requests, all the good open source stuff. Another thing that is targeted more at writers than at software developers is C# Advent Calendar. If you are familiar with Advent calendars held by C# and F# communities, it's a tradition in which in December every day one blogger writes a post about this language, about something they have done with this language, or a feature, or highlighting some kind of tool or library from the ecosystem, something like this. So this is what C# Advent Calendar is. Every day somebody writes a blog post about C# or something C# related. Check out the past calendars. They have some pretty cool stuff in them. Also, the picture of the cat in a scarf is to die for. And of course, you're welcome to look forward to the next Advent calendar and maybe even join. And to round this up, let me show you how other people can take our work and bring it forward to scale it up to reach people who we wouldn't be able to reach on our own. This group is Microsoft Garage India. For those of you who are not super familiar with Microsoft internal structure, Garage is a kind of a team in Microsoft, I guess, who are working on sort of organizing events and hackathons for developers, both inside Microsoft and outside it, and kind of promoting the culture of doer, hacker, somebody who goes in, sees a problem, and solves it. And in this case, the India chapter of Garage is really enthusiastic about quantum computing and our work. And they drive a lot of local events in India. I think they started with just a study group a couple years ago, and now they do online events, in-person events in different places in India. So you can see the number of people they reached. They host online webinars. They hosted in spring. I'm not sure whether they still continue. So, for example, so basically they took the quantum katas and host another webinar around going through them, working on the solutions, working them out and explaining them. So taking our work and taking it to the next level. They established academic partnerships with several universities in India, again, using some of our curriculum materials and kind of digesting them and putting them into the form that they like. They bring quantum computing to universities. And here is the link that you can use to join. I don't think they're limited to just India. So it's mostly if you are close to their time zone, it's going to be more convenient for you than, for example, entirely US-based events. And this is all I have for you now. We might be launching another event anytime now, but I'm not at liberty to talk about it right now, so stay tuned. Meanwhile, some of the things you can do to join our community. Well, the first thing is, of course, learn quantum computing. And once you start doing that, you have all kinds of options open for you to give back to the community. So the contributors guide on contributing to the quantum development kit is at this first link. It takes you through the various open source repositories that we have, because we have multiple for different components of the compiler, the runtime, the libraries, the quantum katas. They're all slightly different. So you're most welcome to start digging around there and checking out the open issues and seeing if you can contribute to any of them. The second link is Q# developer blog. We write about past events. We hold events like Advent Calendar. So it's a good place to be checking out together with our Twitter. And the third link is Q# community, which is a good starting point to discover community-driven engagements. This community, I believe, has been started by Sarah, who I highlighted earlier in the talk, and I think a couple other folks also from the community. And this is all I have for you now. I hope to see you in our community sometime soon. Matt, back to you.
Thank you very much, Maria. Excellent, inspiring session. I hope our attendees enjoyed it, judging by the questions and chats. The answer is yes. So where are we at today? Let me share my screen. Hopefully folks can see that okay. Okay, well, everyone should just take a deep breath. We made it to the end of the day, and I guess you could think of this as the end of your journey just for today. we just have a couple minutes of closing remarks, so I need your attention just for a little bit longer. I know we've been together for a long time, but I think it's important to recap and just make sure that you understand how all this comes together and how you can hopefully take what you learned today and maybe were inspired by today and start to continue your journey. So each of the sessions had specific actions, recommended next steps from them, and you can go back and review those at your leisure once we publish the on-demand content. Probably available by early next week, hopefully by Monday. But here are some things just again to bubble up for you, right? So we learned a lot about how we can drive impact today through, in particular, some of the optimization capabilities of Azure Quantum. So we encourage you to go sign up for that. It's not open to everybody yet. It's in limited preview mode, but we're marching along on our milestones, release milestones for the service. So please add your name to the list so you'll be made aware of as we continue to expand the service. And definitely, as Maria mentioned and many others did along the way, take an opportunity now to learn Q# and how to use what's in the QDK. I think that's time well spent now, so you can prepare yourself for what will be coming in the future as we continue our journey towards scaled quantum computing. Many of you may work for companies and be interested in participating at a partnership sense with Microsoft. Julie introduced the Microsoft Quantum Network to you, so we encourage you to reach out to us if you have interest to participate in that. I mentioned that the content would be available as soon as possible. Look for that early next week. You will get a pointer to it in a thank you mail, and it's actually going to be the same link that you registered at. So we'll just flip that over to providing content. And lastly, and this is really important, I know it's not everyone's favorite thing to do, but we'll be posting as an announcement in the chat right now, a link to a very short survey. So it's, I think it's 7 questions, should take you no more than a couple minutes to fill out. This is extremely helpful for us to get that input from you fresh while it's in your head after just attending all this great content and participating today. So please do take a moment to do that. And with that, I'd like to give a huge thank you to everybody involved in making this event happen, all of our speakers, all of the moderators who have been behind the screen, spending a lot of time doing our best to answer all the great questions you've been posing, and to our great production staff from Event Builders. So thanks everyone for a great effort and everyone's work here today. And with that, I'll turn it over to our production team to say final remarks. Anything to add, Stephanie or Jen on logistics, or are we good to go?
Thanks everyone for joining us today. Please do take a moment to answer the survey questions. And thank you again for joining us for the day, and hope you have a wonderful rest of the day.
Thank you.